Right, apologies everybody about that. Okay, right, I can only see one face, you see, and it's only Max. Right, you can definitely hear me, can't you, Mac? Yeah, right, oh my God. Right, right. So hopefully everybody's getting back on again. Okay, again, apologies for that. Okay, right. I think we're pretty much all back on. So again, apologies, right? I have no idea what happened then. Right, but what we'll do now is we'll just get on. For some reason, I had to just cancel everything to just get it all started again. I'll probably press the button randomly somewhere. Right, so what we're going to do start off with is we're going to think disappearing cross method, right, and why, then analyzing water, okay, and the purification of it, chromatography, and then we're going to talk about concentration of acids, okay? So I'll start working through them, and we'll start off with the disappearing cross required practical. Okay, so what you got to do is you've just got to remember, right, what the kind of practical is about. I'm going to go through sort of the theory behind it about why the actual cross does disappear. Okay, and then what I'll do is I'll come back to the variables. Okay, because we need to obviously know the variables. Right. So, firstly, before I end up starting again, apologies to everybody. I don't know what happened with the sound then. Okay, is this at the top here? That is the equation for the disappearing cross. Okay. Now, as soon as they start to put states of matter into an equation, then they are important. Okay. So this substance here is sodium thiosulfate. Come on, Mac.
Sorry,
Oh,
hello.
right. I'm not sharing, am I? Oh my God. Am I getting old or what? I am getting so old. Right. I can't even. I'm going to start dribbling in a minute. All right. See, if everybody else wasn't hiding, Mac, right, then they'd be able to tell me, wouldn't they? Right, so disappearing cross. So what I've got there now is that equation that I've then circled imaginary in red, okay, at the top. That stuff there is sodium thiosulfate, aqueous, which means it's dissolved in water. So pretty much what that means is you're not going to see it. It's like a clear liquid. You then got hydrochloric acid. Okay, again, it is aqueous. So what it is, it's then dissolved in water. Okay, and I'll just say it again, that if you see state symbols in your exam, they will mean something because they don't put them in every single time. Skip over to the right-hand side. So when sodium thiosulfate and hydrochloric acid react, what they do is they make sodium chloride, which again is dissolved. But the two bits that actually make the biggest difference is sulfur dioxide comes off as a gas. So when you're actually doing it, you actually get a little bit of a smell. Okay, so when you got your face over the top of it, there's kind of a little bit of a kind of an unpleasant smell, and that is the sodium dioxide or sulfur dioxide getting given off. However, the only thing right on that right hand side is sulfur, and it is a solid. That then is the precipitate. So when you get those two chemicals on the left hand side, the sodium thiosulfate and the hydrochloric acid, you mix them together, it forms a precipitate, and that is that there, the solid sulfur. That is what makes it go cloudy. Okay, so you need to genuinely look out for that. What you'll also do, well, in fact, I'll do the method next. Okay, now with the method's quite complicated, right? So what I've got on there is I've kind of got a big, long, wordy method, but what I'm going to do is I'm just going to kind of go through a few of the chemicals that kind of simplifies it. So in experiment number one, we're going to have 10 centimeter cubed of hydrochloric acid. We're then going to mix it with 10 centimeter cubed of sodium thiosulfate. Well, not yet. We're going to get 10 centimeter cubed of sodium thiosulfate, and we're going to get 40 centimeter cubed of water. Okay, so that is then experiment number one. Okay, so you get the thiosulfate in the water, you mix them together, or they might give you a concentrated solution of some sort. Difficult to predict whatever they're going to put. But what you've got then is you've got a low concentration of sodium thiosulfate because you've got less of it. You have those together, You put them in your conical flask, you mix them together, you give it a swirl, you look over the top, and then you wait for the cross to disappear. That's experiment number 1. Now, experiment number 2 is when you get 10 centimeter cubed of hydrochloric acid, but this time you'll have 20 centimeter cubed of sodium thiosulfate and 30 of water. Okay, so what you can do now is you can see that you're increasing the concentration because you've now got more sodium thiosulfate. But you've also got to remember 10 plus 40 is 50, 20 plus 30 is also 50. So one of the kind of variables, the control variable, is the fact that you've got the same volume of liquid in the sodium thiosulfate and water. Experiment number 3, 10 of acid, 30 of thiosulfate, 20 of water. Experiment number 4, 10 of acid, sodium thiosulfate is 40, 10 of water. Experiment number 5, 10 of hydrochloric acid, 50 of sodium thiosulfate, 0 water. Okay, and then what you'll do from that is you'll then get your results, and your results will look approximately like this, where if you've got concentration of sodium thiosulfate is high, which is over on this side here, the left-hand side, the reaction is faster, right? So you've got to think that then the faster the reaction, the higher the concentration of sodium thiosulfate. You'll then get a graph that looks like this, okay? And so what you can do then is you can kind of describe the graph, then you can say, as the concentration of sodium thiosulfate decreases, the time increases. Okay. Now, if I then go back to the actual experiment itself, right, what you've got to do is you're going to think now about what the variables might be. So remember, don't mess in class. The dependent, the one that what we're measuring is the time for the cross to disappear. Okay, don't mess in class. What do we change? The concentration of the sodium thiosulfate. Now, I did it by having the sodium thiosulfate and water, right? But what you might do is they might give you different concentrations. Okay, you've just got to kind of look out for what they do. Control variables, the temperature needs to stay the same. The cross needs to stay the same. The person needs to stay the same. The concentration of acid stays the same. And also the volume of the acid stays the same. Okay, but one of the key things is the person, right? Because if you think, if I was working with one of you, right, and I'm looking down the actual conical flask, my judgment of when it disappears is different. Okay, right, so disappearing cross, I think personally, one of the most important things that you need to know on this one is sulfur. Sulfur is the solid, and that is the precipitate that forms. Right, so that is sodium thiosulfate, disappearing cross. Right, next one is purifying and analysing water. Okay, now the idea of this is that what you do is you get a sample of water, and what you've got to do is you've got to, number one, you've got to analyse it. And number two, you've got to show how you can purify it. Right, so analysing the sample of water, right? So you might get 50 or 10 centimetre cubed of water. First thing you do when you're analysing it is you look for the pH. And to do that, you just get a piece of universal indicator paper, and then what you do is you put it into the water, and then it changes its colour. So you've got to look at pH 7, pH 6, pH 8. Okay, so pH 7 is obviously neutral, pH 8 is slightly alkali, pH 6 is acidic. Okay, if they ask you to improve, then what you do is you get a pH probe. Okay, and the pH probe you'll then put in and you'll get a digital reading. If you get a digital reading, then you have an increased resolution. Resolution meaning it's more accurate, because then you can get like a decimal place. Once you've tested the pH, then what you've got to do is you've got to accurately weigh the evaporating basin to 2 decimal places. right? So you get your evaporating basin, you measure the weight of or the mass of the evaporating basin, and then you've got to accurately measure the amount of water that you put in. So you now know exactly the mass of water. Then, so the idea of this now is you're analyzing it again. So you've done the pH. Now you're going to heat it up. And eventually what you're going to do is you're going to boil all the water off. When all the water is then evaporated, you will then have solid matter left at the bottom. And often what they'll do is they will ask you to then calculate the percentage solid matter. Okay. So this is then again how it kind of works, right? What you have is on the left-hand side, you've then got a beaker and it's got some impure solid at the bottom. Best way of doing it is heat it up to get rid of all the water. Keep on heating it to get rid of more of the water. And eventually what you'll do is you'll get some crystals or solid matter at the end. And you can then work out the percentage mass of solid. Okay, so for example, if your original mass was 100 grams, and at the end you've got 1 gram left, you can then work out the percentage would then be 1%. Okay, so things on this. First thing you're going to do is you're going to look for the pH. Because the whole idea of this is to look at to see if that water is, I guess it's drinkable. So analyze a water sample, look for pH. Then you're going to look to try and find the percentage by mass of solid in that water. And to do that, you boil all the water off and you see what solid you're left with. Okay, that's method kind of number 1. Method number 2 is they might ask you, how do you purify a sample of water? So to purify your sample of water, what you're going to have is you're going to have this piece of equipment on the right-hand side, which is a condenser. Condensor. Okay, and the condenser is sometimes called a Liebig condenser. Okay, and then the way that the condenser works is you heat your water up here, or whatever solution it is. So you could have salt solution. The water boils, it goes into the condenser. Then around the outside of the condenser, you've then got cold water. So you've got cold water at the top and at the bottom. It's like a cold water jacket. When the steam goes into the middle of that cold water jacket, then what happens is the water then turns back into a liquid, dribbles down, and then what you do is theoretically you get 100% pure water going into your conical flask at the end. Okay, so that is then the second method. So the second method is you boil off the water, send the steam through a condenser, the condenser then turns it back into a liquid, and then theoretically you've then got 100% pure water at the end. Then that is analysing pH and the solids in it. And the second one is purifying it using a condenser. This one on the left-hand side, okay, it's more of a kind of a simple version, but it works exactly the same way. But instead of having a condenser, what you've got there is you've got icy water. The icy water cools down the steam, and then it turns it back into water. Okay, right, required practical number 3. So required practical number 3 is then chromatography. Right, now what I did was I kind of did a bit of research into sort of practicals and questions about chromatography. And what they're going to do is they're either going to give you a method, they're going to give you a set of results, or they're going to give you a method that is wrong. All right, so I found that picture there. Okay, and what I normally do is I normally just ask what is wrong with that picture. Okay, and if you do look at it, right, here is your pencil line at the bottom with your kind of coloured dots on it. The coloured dots are below the water, right? So that is then an issue. Now, I'm going to go through the method now. Okay, so just kind of ignore that picture on the right-hand side. So what you're going to have is you're going to have your beaker, and you're going to put your piece of chromatography paper into the beaker. You're then going to put your dots on a line that is, or pencil line, 2 centimeters from the bottom of the chromatography paper. So you get your chromatography paper, you then draw a pencil line 2 centimeters, or what, 2 centimeters from the bottom, or it could be 1 centimeter from the bottom. Then you put your little coloured dots on it, onto the pencil line. That then hangs into the beaker. Then what you do is you put in your solvent, and the solvent must just touch the bottom of the piece of paper. Once that then just touches the bottom of the piece of paper, the water will then naturally go up the chromatography paper and it'll take the dots with it. When the dots get to about 2 centimeters from the top, you pull the water out, you pull the paper out of the water, and then you draw another pencil line at the top, and that is then called your solvent front. Okay, so that is your solvent front. You then have your piece of paper, you've got a pencil line at the bottom, you've got a pencil line at the top, and then in between, you're then going to have all your colours that have then travelled up the piece of paper. Right? Now, what does that actually tell you? We'll talk about the RF value in a minute. Okay. Now, the other thing that you need to remember with chromatography is why do the colours go up at different speeds? So why does red go up faster than blue? Right? And that is all based on its solubility. Solubility. Okay, so the more soluble it is, the further it goes up the piece of paper. Right? Okay, right. Double quickly going to do that again, right? You draw a pencil line 2 centimeters from the bottom of the chromatography paper. Then you put small spots of whatever they're talking about. It could be ink, it could be dyes, along on the piece of pencil line. Put water into the beaker, and then when it's traveled approximately 2 centimeters from the top, you take it out and you draw another pencil line, right? And on the other pencil line, that is then called the solvent front. So that is then where it ended. You then measure the distance between the two pencil lines. I'll show you that on the next picture. And then you can measure something called the RF value. Okay, so this diagram, the line at the bottom, that's your original pencil line. The line at the top is your solvent front. Okay, then to work out the RF value, what you do is you measure the distance the ink dot has travelled. On here it's called X. And you divide it by the distance the solvent has travelled. And on here they're going to call it Y. So if you imagine X on this was 3 centimeters and Y was 6 centimeters, the RF value would be 0.5. Okay? And in your exam, if you ever work out an RF value is bigger than 1, you've done it wrong. And if you work out an RF value and it's less than 1, like into negatives, you've also done it wrong. All right, so that'll be the calculation that'll come up to do with chromatography. Okay. Right. Now, the fourth one, right, which I always find this one kind of a little bit sort of woolly, and it's a bit sort of not quite as precise as all the other ones, is all to do with concentrations of acid. But what you've got to do is you've got to compare potentially reactions of metals, compare the reactions of acids, and potentially even compare things like temperature. Okay, so again, this is quite a difficult one to predict exactly what it's going to talk about. The last time one of these experiments came up, they said you've got 3 test tubes, and in each one you've got a piece of metal, and then you've got hydrochloric acid. You then had to come up with a method that then talks about which one of those metals is the most reactive. Okay, and I'll do that again in a minute. Right, now, the equipment. vast majority of the time, if they then start talking about rate of reaction or concentration or something to do with an acid, this is often the piece of equipment that you're going to need. Okay, so you'll start off with usually an acid, then you'll have a piece of metal. They are then put together, and then what happens is you will get a gas given off. It goes down the delivery tube. This measuring cylinder was already filled with water and turned upside down. The bubbles will then go up the measuring cylinder and they will fill it up. Okay. Now, a number of ways in which you can do that is you can time how long it takes to fill up 80 centimeter cubed. Okay. Or what you can do is you can just do the experiment for 2 minutes. Okay. Now, the problem with doing it for 2 minutes is the fact that it could fill up way too quickly and then you wouldn't have any water left in the measuring cylinder. Right? So what they're actually asking in this is, how does the concentration of acid affect the rate of a reaction? Okay, so think about it now. This is experiment number 1, and let's say we've got 1 molar. You do the experiment. You can then say, you've done this. It took 30 seconds to get 80 centimeter cubed. That is then your result, and you write it onto a results table. Experiment number 2, you might do 2 molar acid. But again, they will give you the actual moles, or they will give you the concentrations. Now, other kind of equipment, if you look down on that right-hand side, right, what there is then there's the same sort of equipment, but this time, instead of having an inverted measuring cylinder, what you've then got is you've got a gas syringe. And what a gas syringe is, it's a syringe, right, that is very, very easy to move. So literally gas that is taken off from the reaction mixture, what it'll do, it'll go down the delivery tube into the gas syringe and it'll move the gas syringe. Okay. Right, now what I'm going to do is I'm going to kind of go through the numbers for the actual method that I've been talking about. Measure 50 centimeter cubed of hydrochloric acid using a measuring cylinder. That goes in your conical flask. Fill the other measuring cylinder with water and invert it in the water trough. Add a single 3 centimeter strip of magnesium ribbon to the flask and start the stop clock. Record the volume of hydrogen gas given off every 10 seconds or every minute, or record the time it takes to get to 80 centimeter cubed. Okay, it's a difficult one again to predict, but if we go with this, record the volume of the hydrogen gas given off every 10 seconds. And then if they're asking about concentration of acid, repeat using different concentrations of acid. Okay, so I'll go through the standard one, right? But I always think that this is one in which they're very awkward with. You've got to kind of predict it. So 50 centimeter cubed of hydrochloric acid using a measuring cylinder. That goes in the conical flask. Fill the other measuring cylinder with water and invert it. So therefore the measuring cylinder in the middle of the screen is full. Add a single 3 centimeter strip of magnesium. Start the stop clock. Record the volume of gas given off every 10 seconds. Put it in a table. Repeat using more concentrated hydrochloric acid. Okay. Now, if you think about it, what they could also do is they could also say test for calcium and iron. And then what you'd have to do, instead of swapping the acid, a piece of metal that goes in the bottom would then be calcium or would be iron. But what you've got to do is you've also got to make sure that you'll do 3 centimeters of calcium and 3 centimeters of iron. So you've got to keep whatever they're asking you for constant. Right. Now, I don't like that last one, right, because it's quite difficult to kind of talk about. You've got to look out for the acid. What are they asking you to change? If they're asking you to change the acid, right, the metal stays the same. If they're asking you to change the metal, the acid stays the same. What are you going to collect? You're pretty much every single time going to collect the gas. Okay. And if you don't collect the gas, you can then observe to see how much gas is actually given off, right? By looking at the amount of bubbles that are given off. Just clicking back on, that'll do then, yeah. Right, now going into kind of the theory stuff, and if I've got time at the end, I'll go through some of the required practical things again. Okay, right. In an experiment, right, if you see your starting mass is 123.45, you then do your experiment and the mass has gone down, what you've got to do is you've then got to wonder why on earth, if you've done an experiment, has the mass gone down? Okay. And basically what's happened is bubbles have given off gas and the gas has come out. Okay. And I've written that here. So in an experiment, if they say the mass is lost, that means a gas has escaped. So in an experiment, if the mass goes down, gas has left. If the mass increases, that will mean gas has entered. Right? And what they'll do is they'll literally just give you kind of a mass balance, and they'll show the numbers on the mass balance, and then it'll look really stupid in the fact that the mass has gone up or the mass has gone down. But that is all to do whether gas leaves or gas comes in. Okay, right, more reactions with stuff. Okay, so what I'm trying to do here is I'm just trying to kind of throw loads of sort of information at you. Right, so what I've got there is there's a graph, okay, and it shows two lines. The red line is your high concentration of acid, and the green line is your low concentration of acid. Right, so let's say what I've got is I've got 10 grams of magnesium. Okay, I'm just making these numbers up now. Okay, and what I do then is I add it to a high concentration of acid. The red line shows the reaction. So what happens is very, very rapidly, the reaction happens. As the magnesium gets used up, it then flattens out. Okay, so that's the reaction with the high concentration of acid. Now, if you use a low concentration of acid, all you got to realize is that the rate is slower. And you can tell it's slower because the graph isn't as steep. However, what they both do is they both end up at the same place. And the reason why they both end up then at the same place is because all of the magnesium or all of the substance that is being reacted is used up. Okay, it just means that with a low concentration of acid, it takes longer to get there. Okay, so look at the graphs, right? And the key to these graphs is the steeper the line, the faster the reaction. But if they get back to the same place, that means one of the substances has been used up. Right. Quick bit of exam terminology. Right. Now I'm chucking this in now, kind of after the practical bits. Right. Now we've talked about these over the year or however long it is. Huge amount. Okay. So read the full question. Right. Now I know you've done 4 science exams and you've got number 5 tomorrow. Read the question. Now, I would, again, I've said it before, I would highlight, I'd look at the actual question itself and literally get a highlighter out and highlight, this is what the question's actually asking me. Okay, so take your time and work it out. Define, definition. Describe, list the facts. Calculate, do a sum. Okay, now the most likely thing you're going to get tomorrow is a graph. Use the graph, make sure you use the graph. If it says use figure 3, make sure that whatever it says on figure 3, you use. So if figure 3 is a table, you use the numbers off that table. If it says describe the trend, you then say the trend is it goes from low to high or whatever it is, but include numbers. right? Because the more numbers that you include in your answer from a figure, from a table, the more chance you've got of getting better marks. Explain, chuck in a so. Suggest is give an idea. Compare, you can say however. I'm including whereas in there, right? But again, don't forget, if you compare, you need to do an right? Faster, slower, bigger, smaller. Now, I think you've already had 2 evaluate questions, but don't forget, evaluate, because and a but, okay? And what you're doing is you're looking for advantages and disadvantages. And your final statement will be, therefore, I think this is the best because. Right? So proper tomorrow. Okay, it's not quite as important as biology paper, but proper look at what they're actually asking you. Right. Theory. Right. So we're going to go down the collision theory route. Right. Why does a reaction happen? Okay, and it's all to do with particles. There are 3 things that must happen. Firstly, for a reaction to happen, the particles must collide. Okay, so if I think about my fists, right, if there's going to be a reaction that's going to happen, they have to hit each other. Okay, because if they don't hit each other, there is no reaction. Number 2, on this left-hand side here, they must be in the correct orientation. So for a reaction to happen, they must collide. They must be in the correct orientation. So my fists are kind of hitting each other, but if it was hitting my wrist, then that is not a reaction. And there's also got to be sufficient energy. So if my fists just slightly touch each other, there is no reaction. Okay, so collision theory. It's all based on particles. Particles must collide. They must be in the correct orientation and they must have sufficient energy. Those 3 things must happen for a reaction. Okay, so honestly, write them down, right? I would generally write them down, right? Because they are important. That's for a reaction. Now, there is 5 factors that affect, okay? Now, there's 4 that are on the screen at the moment, okay? And what I'm going to do is I'm going to go through each one individually, right? So these are the factors that affect the reaction. Now, if they talk about one of these, you've got to explain why in terms of particles. Okay, so concentration first, all right? Example you could use is if you think about your class at school, let's say you've got 30 kids in your class, right? And what the teacher says is stand up and walk around, right? What's going to happen? Some of them are going to collide, right? Quite a lot of them are going to be in the correct orientation. And then if they're walking fast enough, there'll be enough energy. So there will be some reactions. If you then chuck in another 30 students, what's going to happen is there's going to be an increase in the frequency of collisions, which then means the reaction is going to be faster. So if they start talking about anything to do with collision theory, particles, if you increase the concentration, the number of collisions is going to increase. All about the collisions. If you increase the surface area, okay, now this is again, I'm just going to kind of do that quick little surface area sum, right? So that block on the left-hand side is 2 centimeters by 2 centimeters by 2 centimeters. So if I work out the surface area of the big block, so surface area of the big block, surface area one side is 4. So therefore, if there's 6 sides, 4 times 6, 6, 12, 18 is 24. Okay, so the surface area of that cube on the left-hand side, one face is 4, there are 6 faces, so therefore the surface area is 24 centimeter squared. Okay, if I then smack it with a hammer and I break it up into all these little tiny blocks, I can then look at that, and that. So that block there has got a surface area of 1 which is one side, multiply it by 6, tells me that there is 6 centimeter squared surface area in one block. Then, because I've got 8, it'll be 8 times 6 equals 8, 16, 24, 48 centimeter squared. Okay, so increase the surface area, you break it up. Decrease the surface area, you stick it together. If you want to do that Mento trick where you put a Mento into Coke or lemonade or whatever it is, if you just chuck a Mento in, it'll squirt out. If you hit it with a hammer and then you chuck it in, because it's then a powder, it will come out faster. Okay. Another example, because again, people forget about this, right? There's me. Okay. I've got a surface area, which is all the skin. If I've then got me, right, but this time what I do is I chop myself in half. Okay, that's very, very badly drawn. So I've still got all my skin, but my surface area has increased because in the middle there is now the top and the bottom has increased. Okay, right, so back to it. If I increase the surface area, the frequency of the collisions increases because there is more chance of them actually hitting each other. Third one, right? Increase in temperature, right? The example for this is, right, if you're in your class and there's 30 of you and you're all walking around, okay, some of you are going to collide with sufficient energy in the correct orientation. If you increase the temperature and everybody then is running around, because now all the particles have got more energy, there's going to be an increased chance in collisions, right? Because everybody is then moving around faster. So there's going to be more contacts. There is going to be more of every single kind of part of the collision. So if you've got things going faster, there's going to be more contact. There's going to be more in the correct orientation, and they're going to have more energy. So there's going to be more reactions. Fourth one, increased pressure. This is then very similar, really, to concentration. You've got 30 kids in your class. Okay, so if you've then got 30 kids in your class, and then what you do is you half the size of the classroom, what's the chance of being more collisions? Right? You've halved the size of the classroom, therefore there is an increased frequency of collisions because you've got the same number of students in less area. All right, so if I just double quickly click back on this, 4 factors that affect the rate of a reaction, remember them: concentration, and it's all because you increase the frequency of collisions. Surface area, you increase the frequency of collisions. Temperature, you increase the frequency of collisions. Pressure, you increase the frequency of collisions. Right, now the 5th one is a catalyst. Okay, now a catalyst doesn't necessarily increase the frequency of collisions, right? But what it does was, if I kind of draw a graph next to this, that there is a typical kind of reaction curve, where from there to there is the activation energy. All right, so what you've got to do is you've got to put the energy in to make the reaction happen. For me to light a match, I've got to move that match on the kind of the bit of stuff on the side to actually light the match. With a catalyst, what that does is reduces the activation energy. So therefore, the line from there to there is lower. So a catalyst reduces the activation energy, which then means the reaction goes faster. Okay, you need to remember all 5 of them and the reason why you've got collision theory in the first place. Right, state symbols. We kind of mentioned these already, right? So what we've got is we've got 4. Okay, there was an exam question on last year, right? I think it was last year or maybe 2024. And it said, it gave an equation and it said, work out the state symbols. Okay, and basically all the papers I marked, right, people didn't know what state symbol meant. Okay, so state symbol is solid, liquid, gas, or aqueous. Okay, So what you could do, if you're actually given an equation, you need to think about what there could possibly be. If it is a metal, chances are it's going to be a solid. Okay. If it's water, which is probably the main one, it'll be a liquid. There's very few really that come up that are liquids. If it is an ionic compound of some sort, the chances are it's going to be aqueous. So that'll then be dissolved in the water. And if you recognize it as a gas, hydrogen, oxygen, chlorine, okay, all those different things, it's a gas. Okay. Now you've then got to kind of use your sort of general knowledge to then work out which is which. But if it says state symbols, solid, liquid, gas, aqueous. Now again, I said it right at the very start, if they put the state symbols in, they will be part of your answer. Okay, right, a rate of reaction. Right, how do we actually know a reaction is happening? Okay, this is again, it's another good question, right? Probably a 1 or a 2 marker. How do we measure or how do we observe that a reaction is happening? Number 1, a precipitation forms. That is your disappearing cross. So when that solid appears, that solid sulfur appears in the disappearing cross reaction, that is a precipitate. If you think about one of the food tests, right? If you've got the food test where you get ethanol and water and it goes cloudy, that is a precipitation forming. You might get a colour change. Okay? Again, the food tests work quite well with this, where if you've got the Benedict's test and it goes from blue to red, there's a colour change, which means there's a chemical reaction happened. Mentioned this one previously, change in mass. If the experiment gets heavier, that means gas has gone in. If the experiment gets lighter, that means gas has left. Change in mass. That is then all to do with the volume of the gas given off. So if you actually see gas get given off, then that is number 4. And number 5 is then if there's a change in temperature. Okay? Now, don't just work on the assumption that it's going to be an increase in temperature, because there are reactions that are endothermic where there'll be a decrease in temperature. Okay, so how do we observe a reaction? Precipitation goes cloudy. Color change would go from clear to white. Change in mass, if it gets heavier, gas has gone in. If it gets lighter, gas has gone out. You could see the volume of the gas or even bubbles appearing. And the 5th one then is temperature change. Don't just say temperature increases or temperature, say temperature change, because it could get hotter, exothermic, or it could get colder, endothermic. Okay, right, now rate of reaction, right? What they might do is they might ask you to calculate a rate. Now, usually what they do is they'll give you the equation to calculate it. Now, if they don't, I will always go for that little section at the top there. All right, now this is then more likely to be at the end of a higher paper on a separates paper. If they ask you to calculate the rate of a reaction, always think about how much is getting given off in how long. Okay, so for example, if I had 10 grams of substance getting given off in 20 seconds, you can then see that you've got 10 grams of substance given off in 20 seconds. So you'll do 10 grams divided by 20 seconds equals 0.5 grams per second. Okay? So if they ever ask for rate of a reaction, remember it as how much is given off in how long. And there's always got to be a time at the bottom because a rate is time. Just like speed. Speed is meters per second. Okay, that is a rate of movement. Okay. Right. Another reaction, right? A potential one is a reversible reaction. Now, for combined science, you don't really need to know very much about reversible reactions. What you need to do is you need to know what that symbol means, right? And what that symbol means there is that the experiment can go to the right and it can go to the left. What it is, it's a reversible reaction, right? It's not just going one way. So if I set fire to something, it goes from the stuff you burn to something else and you can't get it back again. But a lot of reactions are reversible. That is the symbol for it. Okay. If they showed you as the symbol with a longer arrow, if they showed you a symbol with the arrow being longer at the top, that means there's more likely it's going to go from A to B to C to D than the opposite direction. All right, so if the long arrow is pointing to the right, more likely to go to the right. If the short, longer arrow goes to the left, it's more likely to go to the left. Okay, but at the end of the day, for combined, right, and for separates, we'll go through some of this later. That symbol there means reversible. Okay, that's another example of it. Okay, and that's something called Le Chatelier, right? And that is then mainly, well, it is on separates paper. Okay, but what it does, that is the reversible reaction symbol. Right. Now this is purely higher. Okay. Now, if you are asked to calculate the rate of a reaction, and what you've got is you've got a curve, you need to do a tangent. Okay. So what I'll do is I will show you the tangent in a second. Okay, in fact, I'll do it now. So this graph's a little bit better to look at. So what you've got is you've got your curve, right? So on foundation paper, you're not going to get asked to do a tangent, right? So where you've got that red line, that black line, right? If they ask you to do a rate of a reaction at a certain point, which is there, what you then have to do is you do a tangent. Okay. Now, the actual length of the tangent doesn't really matter. Okay. However, what I would always do is I would always measure from the central point, let's say 6 centimeters, and then going in the same direction the other way, I would also do 6 centimeters. I would make sure that below the point where my tangent touches the curve and above where my tangent touches the curve is the same length. Okay. And then at the ends of those kind of the tangent, I would make sure that the distance from there to there, the end of the tangent to the curve, and the end of the tangent to the curve is also the same. You would then do amount, 0.7, time, 100 seconds. That then gives you your rate, because on the top you put the amount, and on the bottom you put the time. Okay, so I'll just repeat that again. So if you get asked to calculate a rate of a reaction, and it is a curve, you draw a tangent, and then just like in maths, you then draw a triangle, and you put the amount on the top and the time on the bottom. So because this is in grams and seconds, your unit on this one will be grams per second. Okay. Right, on to organic chemistry. All right, now before I move on to the next bit, has anybody any questions about any of the stuff we've done so far? Right, you can unmute or just put a message on. Okay, there's a fair bit, right? And it's kind of, it's not, I like science when it's kind of nice and clear and it's this, and this, but in the chemistry stuff, it's not quite the same. Right, onto organic. Okay, so first thing is crude oil, right? So millions of years ago, tiny marine animals, okay, and I'll write it over here, often plankton, were in the sea, and what they did is they died. Okay, so millions of years ago, plankton, little tiny living kind of creatures in the sea, what they did is they died and they sank to the bottom. When they sank to the bottom, so this is in the second diagram, rock, silt, sand went over the top of them. So plankton sank to the bottom, sediments, sand, different bits of rocks and things like that went over the top of them. Over time, they got squashed and heated up. So they got compressed and they got heated up. That meant that they were then trapped, squashed, heated, and then over many, many millions of years, what they did is they then gradually then turned into crude oil. Right? Now, crude oil, so if that is kind of the surface, I'm just kind of doing it on the right hand side of it, right? If that's the surface of the ground there, and then what you've got is you've got your, I'll do it in black, makes sense. Okay. And then what you've got is you've got your layer of oil underneath the surface. What you've also got to make sure, and these places they have something called a cap rock. What a cap rock is an impermeable layer of rock. So the crude oil forms underneath the ground. That then gets trapped underneath a rock that is called a cap rock. And if the cap rock isn't there, the crude oil just seeps out. Okay. Then what we do is we come along, we drill through the cap rock. Firstly, we then find natural gas, which is a pocket at the top, and then we can get our crude oil out. Okay. It always amazes me how they actually do get the crude oil out, right? Because if you think what they're going to do is they're going to drill down about a mile, right? Can be a mile, can be a mile and a half, could be 300 meters, it could be kind of anything. We don't have pumps that are then strong enough to suck it out. Okay? Literally, there isn't anything strong enough to suck it out. So literally what they do is they then pour water in. Okay, so if you imagine now, if they pour water in, oil floats on water. So as you put the water in, the oil floats on it and the oil comes out. And when all the oil is then finished, all out, then it's just full of water underneath there. Okay, so that's crude oil. Coal forms in pretty much the same way. Okay, so what we've got is we've got millions of years, plankton sinks, gets covered over with sediments like sand. It then gets trapped underneath the ground under cap rock like impermeable rock, and then we can then pump it out. Right. Alkanes and alkenes, they are the combined ones. So an alkane is single bonds and it is saturated. Saturated means that every single carbon is bonded to 4 other things just with a single bond. Okay, right. So they're saturated, and the first one in the series is then methane. These are then the first 4. So we've got methane, ethane, propane, butane. Methane, 1 carbon, ethane, 2, pro, 3, butane, 4. Okay. After butane, it gets easier because then what it does, it goes to pentane, hexane, hept, 7-ane, oct, non, dec. All right. And literally what those numbers mean, or those words mean, is the number of carbons in there. So meth is 1, eth, prop, but, pent, hex, hept is 7, oct, non is 9, dec. And the displayed formula on that right-hand side there shows that it is an alkane because there's no double bonds in it. Okay, right. That is then the general formula for an alkane. Okay, it's a bit like your nth term in maths, where if I said to you, your alkane has got 72 carbons, it would be C72, H72 times 244 plus 4, 146. So that would be then the name or the compound for an alkane, formula for an alkane. So an alkane, CN2H2N plus 2. Alkenes, right, are a little bit different in the fact that they've now got a double bond. Okay, a double bond meaning there's 2 bonds between a carbon. Okay, and if you look at propene, because the ending now becomes ene, propene's got 1 double bond, and the other carbon is just got the normal number of bonds that it might have around it. Okay, Right, now, another thing just to note is you're never ever going to get methane, right? Because if you think methane is one carbon, it is impossible to get a double bond to methane. General alkene formula, CnH2n, right? So all you've done then is you just got rid of the +2. So if I wanted an alkene that had 7 carbons in it, it would be C7H14. Okay, so that is then the formula for an alkene. Bigger versions, alkanes are saturated. Saturated meaning that all of the bonds have got one single bond to all the others. Unsaturated means there's double bonds in it. Test. Okay, now this test, I'm sure it came up 2 years ago, right? And what it was, it's the test for an alkene. So what you do is you start off, this yellowy liquid there is called bromine water. Okay, you don't just call it bromine, you call it bromine water. If you bubble an alkene through it, which has got a double bond, it goes colorless. Okay. If you bubble an alkane through it, it doesn't do anything. Right? So the distinguishing test between an alkene and an alkane is you have bromine water. If you bubble an alkane through it, nothing happens. If you bubble an alkene through it, it goes colorless. Okay, good test. 2 years ago it was on. Okay, right. Fractional distillation. Okay, so what I'm going to do is I'm going to put the fractionating column up, okay, which is there. All right. Now, what you can do now is you just got to kind of picture a little bit then what goes on. So down on this bottom right, left-hand side here, you put the crude oil in. Okay, you put the crude oil in as a vapor, and it goes in very, very hot. Okay, so I'll just turn it to green. It goes in very, very hot. At the bottom, what happens is, if at 300 or whatever temperature it is, it then should be a liquid, it sinks to the bottom as a liquid. If when it goes in, right, it's still warm enough to be a gas, it travels up the fractionating column until it gets to the point where it turns back into a liquid. Okay, so at 270 degrees C, the fraction here becomes a liquid, which is then diesel. If it still isn't a gas, or it still isn't a liquid, it keeps on going up until it gets to kerosene, 170. And it keeps on working its way up until petrol, 70 degrees C. Okay, now you don't need to know all the temperatures and all those different things like that. What you need to do is you need to know about the reason why. Okay, and what I'm going to do now is I'm just going to go through it. Okay, now just while I have a swig of drink, okay, what I want you to do is just have a quick read through that, okay, which is then kind of an explanation of fractional distillation that I then just kind of talked about. The fractional distillation is all to do with the boiling point. Okay, right now they might ask you a little bit about that, but the main thing they're going to ask you about is why. Okay, now what I'm going to do first is I'm going to kind of I'll just give you kind of an analogy first. Right, if you think tonight, right, after you finished here, what you're going to do is you're going to have spaghetti. Right, you're not going to have anything else on it at all. You're just going to have boring white spaghetti. right? You eat your boring white spaghetti tonight, and then you don't eat it all. So then you put it in the fridge for tomorrow. You get up in the morning, and then what you want to do is you want to eat your spaghetti, okay? But when you start to try and get that spaghetti and trying to break it up, you can't get it apart, right? Because all the spaghetti is kind of all linked and gone mushy and goo together. Okay, so they are then long strands of spaghetti. Then what you do is your mate who happens to live with you, they have pasta shells. Okay, so what they've then done is they've had pasta shells. There's no sauce or anything else on it, right? They've eaten half of their pasta shells, then they've got bored, and then tomorrow morning for breakfast, they're going to get the pasta shells out of the fridge. Can they separate out the pasta shells? Yes, right? Not totally easily. Then what you got to do, you got to think pasta shells are small, spaghetti is long. Okay, so the big difference between the two, okay, is the size of the actual molecules themselves. Now, that's kind of like an analogy to think about. So if I go to this diagram, it's a bit kind of complicated, right? But what you can do is you can see there's a big black line chain going all the way down there. That is your big long piece of spaghetti. There's another big long chain going along here, which is another big long piece of spaghetti. In between those long pieces of spaghetti, there is lots of intermolecular bonds. Right? It doesn't necessarily mean to say they're strong, it just means there's lots. So every single red line on there is an intermolecular bond between your long chain of carbon, because each one of those black circles there is a carbon. Okay, and that then is the analogy with spaghetti. So where your spaghetti is kind of all mashed up together, in between the strands of spaghetti, right, what you've got intermolecular bonds, but they're not necessarily strong. You've got a lot of them. With your pasta shells, right, what there is then is because they're small, there is much less, fewer intermolecular bonds. Okay, so you can then separate them easier because there's very few of them, intermolecular bonds. Okay. Now, what you've got to do now is you just got to think about, and I'm going to put up some examples in a minute. You've got to think if you've got long chains, it's hard to separate them. If you've got short chains, it's a lot easier to separate them. Okay, right. So what I'm going to do now is I'm going to go through 4 examples. Okay. On this left-hand side here are the short chains, right? And I'm just going to make you think petrol. Okay, petrol is a short chain hydrocarbon. A long chain, we'll call it bitumen. Okay, so bitumen is the black stuff that you put on roads. Okay, so picture petrol, you can easily pour it into your car, nice, clear, runny liquid. Bitumen, thick, treacly, goes on roads and eventually goes hard. Bitumen long chain, petrol short chain. And now what I'm going to do is I'm going to talk about boiling point, volatility, viscosity, and flammability. Okay, they are kind of the 4 main sort of terms that they're going to ask you about, potentially to do with intermolecular bonds. Petrol has a low boiling point because it has very few intermolecular bonds between the chains. Bitumen has a very high boiling point because it has a lot of intermolecular bonds between the chains. Okay, think about your spaghetti. Bitumen spaghetti, petrol's pasta shells. Volatility. Volatility is the tendency to turn into a gas. Okay, petrol very easily turns into a gas because it has very few intermolecular bonds, so it can separate easily. Bitumen is very difficult to turn into a gas because it's spaghetti and it's got lots of intermolecular bonds. Viscosity. Viscosity means how easy it flows. Petrol has low viscosity because it has few intermolecular bonds. Bitumen has high viscosity because it has a lot of intermolecular bonds. Okay, again, don't forget, it's not the strength of them, it's the number of them. Flammability, petrol is highly flammable because it has few intermolecular bonds. Bitumen is very inflammable, right? Because it has a lot of intermolecular bonds. Okay, right. So again, I can't predict questions, right? But what they're going to do is they're going to talk about different fractions. They're going to talk about petrol. They might talk about kerosene. They might talk about naphtha, which is in the plastics industry. They might talk about diesel. But what you've just got to remember is you've got to remember that the longer the chain, the more intermolecular bonds there are. Okay. So if I then show you the diagram, or wrong way, if I then show you the diagram here again, those carbons, those black circles is the chain. Okay, so that one there is probably about 20 carbon chain, maybe even more than that. This one, 2 carbon chain. So the smaller the chain, the less intermolecular bonds. Right. So what I've got on there is I've got size, we just talked about it, boiling point. Okay, so petrol, it's all because of intermolecular bonds. Now, the only other one I didn't have on there was color. Okay, the longer the chain, the darker the color. The shorter the chain, the lighter the color. Think about petrol. Petrol has got a slight kind of yellow tint to it. Short chain, low or few intermolecular bonds. Bitumen, long chain, very dark. Okay, all about numbers of intermolecular bonds. Okay, right. Now, what I've now got is, I just kind of give an example again. So what I've now got is I've got a chain length of bitumen and it's like, I don't know, 600 carbons long. Okay, if I got a chain length of 600 carbons long, right, vast majority of the time it's useless to me. I don't really need very much of it. So scientists these days, what they do is they go through a cracking process. Okay, and what cracking is all to do with breaking long carbon chains into smaller, more useful carbon chains. Okay, now the example I've got on here is decane. Now decane is probably not far off petrol, right? But what you can do is if you heat it, you crack it with a catalyst, then what you can then do is then you can produce smaller carbon chains that are then more useful. And also in the cracking process, you can also produce ethene. Ethene is used in the plastics industry. Okay, so think about it now. You've got a massive, great big long carbon chain. What you want to do, you want to break it up. And when you break it up, that's called cracking. That is by heat and a catalyst. When you crack it, you then produce smaller carbon chains that are more useful. And ethene, which is one of the main chemicals in the plastics industry. Okay, this is why in kind of this Strait of Hormuz, right, where Iran and all that kind of stuff is, everybody always talks about the crude oil. Obviously, we need the crude oil out, but also in those countries, what they are also doing, they're doing a lot of cracking and they produce a lot of ethene. Okay, and what the Americans and the Chinese want is they want that ethene out, because if they don't get the ethene out, they can't make plastics. Okay, so that's almost as valuable as the actual crude oil itself. Okay, right. So cracking, right, that could potentially be a piece of equipment that you might have used in school, right? So what you've got here is you've got a Bunsen burner, and on the left-hand side, you've got paraffin. Okay, paraffin's a relatively long kind of carbon chain. And what you do is you heat up the paraffin, which is then kind of soaked in a bit of kind of mineral wool, looks like cotton wool, but it doesn't burn, over porcelain chips. So when the paraffin turns into a gas, it goes over the porcelain chips. And then what it does, it goes down the delivery tube into here. And then what you do is you then have cracked it and you get a gas that is then produced in there. Okay, right, combustion. Okay, so we're getting on to kind of the next topic. All right, where what we've got is we've got methane and oxygen makes carbon dioxide and water. Normal kind of combustion. Then you got your key stage 2 combustion triangle. For something to burn, you need oxygen, you need heat, and you need fuel. Whoops. Okay, and fuel. Okay, so for example, if I had a match, okay, and I just held a match there, right, there is fuel, there is oxygen, but there's no heat. If I had the match and I lit it, right, there is oxygen, there is heat, and there is fuel, right? But if I take the oxygen away, it goes out. So for fire, you have to have all three of those: oxygen, heat, and fuel. So fire extinguishers, like carbon dioxide fire extinguisher, takes away the oxygen. A water fire extinguisher takes away the heat. Right. Now, two types of combustion. Okay, we've got complete combustion, where there is enough oxygen. It's basically the equivalent of aerobic respiration. Incomplete combustion, which is like anaerobic respiration, but it produces carbon monoxide and carbon. Carbon monoxide is a deadly poison. Okay, so if you do incomplete combustion, carbon monoxide is made. And what carbon monoxide does is where we are all sat in our respective rooms, okay, and we're breathing in oxygen. The oxygen joins to the hemoglobin. It then goes around your body, takes the oxygen to wherever it needs to be, deposits it, and then it goes back and gets some more. The biggest problem with carbon monoxide is that when you breathe it in, it goes into your hemoglobin rather than oxygen, but it stays there. It never comes out. Therefore, when your hemoglobin goes around your body, it doesn't pick up any more oxygen. Eventually, you suffocate because your red blood cells then can't pick up any oxygen. Okay? That's why you should have your boiler tested. That's why you should have a carbon monoxide tester next to your fire in your lounge. You should have a carbon monoxide tester next to your boiler. Okay? Because if they go off, you're in trouble. Also, incomplete combustion is producing carbon. Carbon is seen as a particulate. Particulate. All right? Think about your Bunsen burners at school. When you got your Bunsen burner on blue, that is complete combustion because you've got the hole open at the bottom. If you then turn it to an orange flame, that is incomplete combustion. And if you look carefully, you would see black smoke coming off the top. That black smoke coming off the top is carbon particulates. If you put an orange flame under a beaker, it goes black. That's because of the carbon particulates. And also, you've got to remember that carbon monoxide was being made as well. Right, chemical analysis. Okay, so what we're doing now is we're kind of shifting on. Okay, right. What is an ore? Okay, what is an ore? Okay, now on the screen, what I've got is I've got three ores. I've got gold ore, iron ore, and copper ore. Okay, now the little definition that it's actually got down there is it says there a rock with gold in it. Okay, iron ore is a rock with iron in it, and copper ore is a rock with copper in it. Right, now that's great. However, there's a little bit more to it than that. If I dug out some gold ore out of the ground, that's fine, right? Because gold is just there as an element on its own. Iron ore, right? I could go in my back garden now and I could pick up some rocks and have iron in it. Okay. But what I wouldn't do is I wouldn't use that to get iron. Okay. So what I've got is I've got a rock in my back garden. Okay. And for me to get the iron out, it's going to cost me 100 quid. However, the amount of iron I get out of it is 20 quid. So therefore, what a waste of money. Right, so I've got a rock in my back garden. For me to heat it up and get the iron out, it cost me 100 quid. Then I only get 20 quid's worth of iron. Waste of time. An ore would be £100 to get the iron out, but then I would make £300 from the amount of iron. So basically, what an ore is a rock where it is financially viable. And I always say financially viable, sorry. I always say financially viable. So it is financially, right, viable rock. Basically means there's enough rock or enough iron in it to make it worthwhile getting the iron out. Okay, so if they start talking about ores, they're talking about money. Okay, right, metal extraction. Okay, so we're going through huge amounts of things here very, very rapidly. Okay, now there's a number of ways, and we've kind of talked a little bit about metal extraction previously. Right, now that diagram there, it's kind of got our reactivity series. Now it's not please stop calling me a careless zebra, okay, which would be quite useful to do. Right, this is now talking about how we extract metals from our ores. Now, the one that matters is carbon, okay, and that's why carbon is on the reactivity series. There's another kind of invisible line at the bottom here above silver. Okay, but what you got to do is you just got to remember, right, how we actually get hold of these metals. Everything above carbon, that means carbon is less reactive than them, we would use electrolysis. Okay, we would use electrolysis. Okay, now that costs a lot of money, it's very expensive. Okay, so anything above carbon on the reactivity series, if we want to extract it, we use electrolysis. Now, I'm not going to go through the whole process of electrolysis. Anything below carbon and down to silver, we use something called, oh God, the blast furnace. Okay, and what the blast furnace is, where you get your ore, so let's say it's zinc ore, you heat it up incredibly strongly with carbon. So you heat it up with the carbon, with the zinc ore. The carbon displaces the zinc, and then you get molten zinc coming out. Okay, so above carbon is electrolysis. Below carbon is the blast furnace, which is heating up the ore with carbon. Now, we don't need to know all the chemical kind of processes that go on with that. Okay. The third one is silver, gold, platinum. They are actually just found in the ground as pure elements. So if you know where to go, what you can do is you can literally dig gold out of the ground. Okay, and you can find it as nuggets or little seams of things. And you can do the same thing with silver, but obviously silver's harder to see because it's kind of similar sort of color to the ground. Okay, now other ways of extracting metals. All right, now I don't think they're going to ask you about the blast furnace, and I don't think they're going to ask you about electrolysis. Okay, but you kind of need to remember those. There's two other methods. One is called phytomining, and one is called bioleaching. Okay, now these words, right, are highly likely, I think, to come up. Right, so what they do is in phytomining, they get a certain plant, and what they do is they plant that plant in an area where, or in a soil that's got a large amounts of a certain metal. So, for example, it could be in an area that's got loads of copper. It could be kind of an area of land where there's been kind of rocks and all sorts of things deposited on it. Then what happens is the plant absorbs the water and the minerals, but it also absorbs a lot of copper. Therefore, in the leaves, there's kind of more copper than you might expect. Once the plants have got to a certain height or a certain size, And what you can do is you can see those little blue dots have been taken in. They are now on the actual plant itself. When they've got to the right sort of size and they judge it, then what they do is they burn them. So they burn away all the organic matter, and what it leaves is it leaves the metal. Okay. Now, unfortunately, it's not the pure metal. Okay. But what they can then do is then they can use chemical reactions with acids and things like that, and then they can actually make copper itself. So that is called phytomining. Now, the second one is then something called bioleaching. Okay. And then bioleaching sort of works in the same sort of way, where what you might do is you might get a liquid that looks like that, that's copper sulfate. You put bacteria in it. The bacteria then absorb the copper from the copper sulfate. And then you do the same thing again, where you take the bacteria out, and then you heat up the bacteria, burn off the bacteria, leaving the copper. Okay, so you've got two techniques there. You've got phytomining, and you've got bioleaching. Okay. Another extraction method, okay, is what you might have is if you one of those people that like takes loads of metal and stuff like that to the scrappers. Okay, I've done it a few times, got some lead that I've kind of got hold of, or a load of copper wire and copper piping that's kind of been taken out of something, and it's just like a big mess, right? And it's covered in kind of corrosion and it's got rubbish and all that sort of stuff in it. What they do to actually extract those metals is they'll get all the copper, or they think is copper, and they'll mash it into kind of like a big kebab. Okay, because I guess that's what kebab is really. Kebab is just kind of random bits of meats like human and rat and stuff like that. Okay, and what they'll then do is they'll then squish it all together, and they will do electrolysis of it. And if you see on the actual diagram itself, where on the left-hand side there is a big kind of lump of impure copper. Then what they'll do is they will then do electrolysis, and the impure copper goes into the blue solution, and then it comes out of the blue solution onto the other electrode. Okay, so you get all the copper, all the waste copper. They do electrolysis of it, where you've got your impure copper with loads of rubbish else in it. The copper 2+ ions come out of the electrode, the left-hand one, and then they get deposited on the right-hand side, and then all the sludge eventually falls off and it purifies it. That's also what they do with electroplating. Okay, so if you've got let's say you've got a silver ring, okay, and it's an electroplated silver ring, what they'll do is they will have a piece of silver, okay, in a liquid, and then what they'll do is you have a ring hanging from another electrode. You've then got a silver compound, silver compound. They'll do electrolysis, and the silver will then pass from the piece of silver into the liquid, and it'll electroplate onto your ring. Okay, so that is then where what they can do is they can get a very, very thin piece of silver, or thin layer of silver all the way outside of a ring. It's electroplating. Okay, it's the same method for extracting metals. Okay, right. I'm just going to have another drink. That's mad, isn't it? I've never ever teach like this ever in a classroom, because I've literally talked for an hour and a half. Hey, how can anybody concentrate for an hour and a half? So I'm assuming that there's only Mac who's actually awake. Everybody else is asleep. Do you reckon that's true, Mac? Everybody else is there snoring away in their PJs. Okay.
Maybe they're just shy.
They're shy. Are you the only one that's not shy? Okay. There's nobody else brave enough to put their beautiful faces on the screen. It's just you. It's true, isn't it? You're all shy. Zara's the shy. Oh, here we go. Farhan, you're not shy, are you? There we go. Look at
I
that.
never. My camera just wasn't working.
Oh, it wasn't working until that very
Yeah,
moment.
yeah, that is crazy,
That's
isn't it?
remarkable. Remarkable. Well, on Sunday night, everybody's got to put their cameras on. Okay, because that'll be the last session ever. Okay, even you, Zara. You hear that?
My camera doesn't work.
Yes, it does work.
No, it doesn't.
Yes, it does. You've got a mobile phone. I'm using my mobile phone and that works. So shut up. Okay. So on Sunday night, I want all the cameras on. Okay. Anyway, thank you, Farham. Right. Just the best looking people. That's what it is. Yeah. Everybody else is proper ugly, aren't they? Is that right?
Yeah, yeah.
Right. Just me and you two. We're the good looking ones. Unless anybody else wants to join us, of course, and then they could be good looking as well. Anyway, I just lost the plot then for a second. Okay, but like I said, I wouldn't normally teach like this. I wouldn't normally teach like this because this is just me wittering. Okay. Right, so we're still moving on. Oh, Samuel, are you coming on as well? No? Okay, I'm not sure what happened there. Right, so we're about literally 3/4 of the way through the kind of, well, 2/3 of the way through the combined theory. All right. So we are going to now talk a little bit about atmosphere and we'll talk about purity. Okay, so purity. What you have is you might get asked kind of not necessarily test for how pure something is because that's quite difficult. But what they might do is they might give you a graph or they might ask you a little bit about how you can tell if something is pure. Okay. Now, my stupid anecdote that I'll always talk about this time is, right, if you go down the local pub and you go and get your normal stash of cocaine from the local pub, okay, how do you know it's pure? How do you know there's actually any of it in it at all? Okay, do you know anything in it at all? Right, it could be talcum powder, it could be anything. Okay, now obviously you're not going to be able to go home and you're not going to be able to test its purity, right? However, right, if you then are given a graph to look at the purity, a pure substance looks like that graph there, where what you've got is you've got a line that goes up and then it is flat. Because if it is a pure substance, what that means is it all melts at exactly the same temperature. Okay, so if you've got a straight line, that means it all melts at exactly the same temperature, meaning it's pure. If you get a graph like this one on the right, okay, that then is a curved graph. And because it's curved, it means there's loads and loads of other different substances in it. Okay, so it doesn't melt at the same temperature because the impurities in it, they don't allow it to all melt at the same temperature. Right? That is then the main reason why in the winter they chuck salt onto ice. So not only does the salt reduce the freezing point, right, it also means that the water doesn't just freeze at a certain temperature. It kind of makes it impure. All right. Next bit is formulation. Now, when I said right at the very start about exam technique, formulation, there's a great definition. A formulation is a mixture that has been designed as a useful product. Okay, right, so baby powder, right? If you, I don't mean as in like milk powder, all right? So if you go and buy blue powdered milk, right, for babies in a supermarket, right, it will always be exactly the same formulation as in percentages as it is in the next shop over. If you take a paracetamol, it has always got the same amount of paracetamol in it. If you take Calpol, if you're still into that, right, a bottle of Calpol will have exactly the same formulation as in the chemicals that are in it as the Calpol in France, potentially. Okay. Paint. Paint is a fantastic example again in the fact that if you buy Dulux bright white paint in B&Q, Dulux bright white paint in Wix will be the same. Okay, so a formulation is a mixture that's been designed as a useful product. Okay. Right, gas tests. We did one test before, which is this test for ethene. Okay, so ethene is bromine water. Bromine water goes from orangey to clear. Gas tests, hydrogen, you put a burning splint in it and it makes a popping sound. Don't call it the squeaky pop test. Okay, describe it by saying you put a burning splint into it and it makes a pop. Oxygen, you put a glowing splint into it and it relights. Chlorine is litmus paper. Now, if you notice underneath that, I've put damp. If you just put litmus paper, so dry litmus paper going into it, the chlorine won't do anything to it at all, right? It will just kind of be there. So litmus paper must be damp, right? And what it does then, it bleaches the paper. Carbon dioxide, you pass the carbon dioxide through lime water, it goes cloudy, and that is then when you're getting your precipitation. Okay. Right, atmosphere. Right, now, before I start talking about the atmosphere, there's kind of a little bit of repetition that's then going on, is the atmosphere, you're going to get asked about photosynthesis and respiration. No doubt about it. Okay, so at the top there, I put photosynthesis, carbon dioxide, water, light, chlorophyll, makes glucose, C6H12O6, plus oxygen. All right. If they ask for the actual formula itself, make sure you put the sixes, but I'd be very surprised. And then don't forget, respiration is exactly the same thing, but the other way around. Okay, right, now, there's good reasons why I've just talked about those, okay, because we're now going to talk about atmosphere. Okay, right, now, the atmosphere today is those percentages. Right, now, in your exam, they might give you slightly different numbers, okay, but they are generally there. Nitrogen, 78%. You're breathing that in right now. Oxygen, 20.9%, 21%. Other gases, the other main two gases are argon and carbon dioxide. Now, carbon dioxide is normally 0.04% or 0.03%. Now, that is today. Now, the question they're going to be asking you is, how did it go from however many billions of years ago, when Earth kind of appeared in the first place, to now, right? So, Earth's early atmosphere, right, literally when it was just kind of forming, it had nitrogen, ammonia, highly toxic, methane, highly flammable, 95% carbon dioxide, and a bit of water. Okay, that was what Earth was like when it just basically formed. And then just think about what it's turned into now. So the question they're going to ask you about is, how did that happen? Okay, right. Now, what I've done here is I've done kind of a little flow diagram. Okay, so what it does is 4.6 billion years ago, which is basically the age of Earth. During the first billion years, right, there was molten rock, volcanoes, very dry. There was pretty much no water literally on the surface because the Earth was so hot. There was carbon dioxide, water, nitrogen, methane, and ammonia in the atmosphere. That's for the first billion years. So dry rock, volcanoes, carbon dioxide, water, nitrogen, methane, and ammonia in the atmosphere. Okay, totally unlivable to us. As Earth cooled, it rained. Okay, and when it rained, they say it rained for thousands of years, okay, which is even worse than the UK. Okay, right, now if you think about it, the Earth was rock, volcanoes, no water. That means a hell of a lot of rain to make the oceans, like the Pacific and the Atlantic Oceans. So that is then why they say it rained for 1,000 years. Now, during that rain period, what it did, it dissolved a lot of carbon dioxide. Rain comes down, picks up the carbon dioxide as it comes down, dissolves it, and it stays in the sea. So therefore, carbon dioxide percentages are decreasing. 2.7 billion years ago, algae and plants appeared. Now, however they appeared, it's entirely up to you, right? But by the kind of all the genetic material that may well have been created at the time, okay, that then made photosynthesis and oxygen started to be created, which again reduced carbon dioxide levels. So if you look, the whole point in this is to go from 95% carbon dioxide at the top to 0.04% carbon dioxide, which is what we have now. So the rain took a load of carbon dioxide out, algae and plants took a load of carbon dioxide out, and then it was then also stored as coal and oil. Okay, so if you think about the three places now where carbon dioxide is stored: the seas, plants, coal and oil. Okay, they are three of the big ones, and we'll talk about another one in a minute. After 4.6 billion years, we've now got the atmosphere that we now live in. Okay, so I would strongly recommend that after we've finished here today, you have a good look down that. Okay, I've been wrong with every single prediction so far. Okay, however, it's a pretty good chance. 4.6 billion years ago, molten rock, volcanoes, CO2, water, nitrogen, methane, and ammonia in the atmosphere. Cooled, so it rained. And a lot of the carbon dioxide then got dissolved in the seas. Algae and plants also reduced the carbon dioxide. Algae and plants died and became coal and oil, stored carbon dioxide. Now, what we've got is we've now got our current atmosphere. Right. Okay, right. Next bit. Carbon cycle. Talked about it previously, right? So what we've got with the carbon cycle is they're going to ask you something to do with it. Okay, and most likely ones: photosynthesis, respiration, combustion. Right. So if they talk about the carbon cycle, they are expecting three of those words: photosynthesis, respiration, combustion. Right, because they're all to do with photosynthesis, taking the carbon dioxide out. Respiration is putting carbon dioxide in. Combustion is the burning of fossil fuels. We then you may well then get decay. And decay is then when something dies and then it gets kind of rotted away. Right. This is then what I mentioned before: carbon dioxide locked. It's locked in the sea, it's locked in coal and oil, it's locked in plants, and it's also locked in sedimentary rocks. And most of the sedimentary rocks were shells. So again, what happens with the shells? The shells fall to the bottom of the sea, just like coal and oil. Layers land on the top, and eventually what they do is, by heat and pressure, the shells also turn into rock, which is sedimentary rock, and they contain a lot of calcium carbonate. That is then a store of carbon dioxide. Okay, greenhouse effect, global warming, climate change. Okay, so the greenhouse effect causes global warming, which causes climate change. Okay, have a double quick read through that there about the greenhouse effect, please. Okay. Right. Sorry, I had to change the wire on my mobile phone. I think my daughter, as daughters do, is she's stolen mine and put her broken one there. Okay, right, so that's a greenhouse effect. So sunlight comes in, right, easily gets through the atmosphere. Then when it hits planet Earth, what it then does, it turns into infrared radiation. The infrared radiation goes up, it gets stuck under the greenhouse gases, which is mainly carbon dioxide, water, and methane. Carbon dioxide from the burning of fossil fuels. Methane is from cattle like cows, right, and paddy fields, which contains rice, because rice gives out carbon dioxide, and then water vapor. Then that is then collected underneath the greenhouse layer, stays there as a blanket, okay, and then eventually the infrared radiation, because it can't get out, causes global warming, which eventually causes climate change. Okay, now this diagram I've kind of put up before. So global warming is caused mainly by greenhouse gases. Okay, and that is caused by us burning fossil fuels. Now you've also got to remember that deforestation, taking the trees out, not only are we taking the trees out and releasing carbon dioxide, it also means that carbon dioxide is not taken out. What does global warming cause? Climate change. Climate is changing, and we're going to get more droughts. We're going to get rising sea levels. So wherever you live, right, if you're closest to the sea, right, or at a low level, right, you're at risk. So if you're London based, right, then London is one of those places that's actually very, very low. Okay, if you think about the Thames, right, the Thames is not that low, right, below kind of the centre of London. The solutions: more trees, better energy. Okay, so the main solution for global warming is use solar panels, wind turbines. Why don't we do it? Because we don't know, or it costs too much money. Okay, so if it starts talking about anything to do with the greenhouse gas, greenhouse layer, global warming, okay, think about the causes, what effects, what can we do about it, and why don't we do something about it? Right. A few more topics. Okay, so now what we've got is we've got the carbon footprint. Okay, so the carbon footprint is a measure of the amount of carbon dioxide released into the atmosphere as a result of the activities of a particular individual, organization, or a community. Okay, so there's a carbon footprint for me doing this thing tonight. Okay, so I've been talking for 2 hours, right? I've used electricity, you've used electricity, we've used the internet. Okay, there's all sorts of different things that are then being used. And so what that is as a particular individual, guess that's me, right? That's a carbon footprint where we have released carbon dioxide. So the carbon dioxide is the amount of carbon dioxide released as a result of something that has happened. This black pen has a carbon footprint. Okay, it's the amount of carbon that is then required to get from wherever it was made, its manufacturing, to me. Okay, pollution, right? There's 5 on here that we kind of need to think about. Carbon dioxide causes global warming. Carbon monoxide is a pollutant and it's toxic and binds to hemoglobin. I talked about that before. Nitrogen oxides can trigger asthma. Often nitrogen oxides have come out of car exhausts because they're kind of under high pressure at high temperatures. They can also cause acid rain, which then can be kind of nitrous acids. Particulates, I'll talk about that a little bit in a minute, but basically that is then global dimming. Sulfur dioxide also can produce acid rain, whether it is sulfuric acid or sulfurous acid. So it could be a weaker version of sulfuric acid, which is sulfurous acid. Okay, so they are the big 5 main kind of pollutants: CO2, carbon monoxide, nitrogen oxides that can cause asthma, particulates, and sulfur dioxide. Okay, right. Global dimming. Basically, what global dimming is, if you, I mean, I don't live that far from Manchester, and so what you do is you kind of drive down the M6, right, near Manchester, and you go over this big bridge that's kind of goes over a big viaduct, and you look out over Manchester, and Manchester is grey. Okay, and then you look to kind of the left or the right, and you can see the Peak District, which is green, right? And the grey bit is global dimming, which is the particulates that are in the atmosphere around kind of the city. Okay, and what that does is it means that when you look up, your particulates are then blocking your view of the sun. So that is then global dimming. Okay, acid rain, often nitrogen oxides and sulfur dioxide, they go up into the air, join with the water in the air, the wind then blows it over to certain other countries potentially. It always used to be all the pollution that the UK used to make, it used to go up in the atmosphere, and then because of the winds, it used to get blown over Norway and Sweden, right? And then Norway and Sweden used to then get all our pollution, and it used to rain down and kill all their plants. Okay, so acid rain. Fuels, we've got non-renewable, coal, oil, gas, and then we've got renewable. Okay, now if they do start talking about renewable and non-renewable, right, the words that you need to include is replenish. Okay, so non-renewable cannot be replenished. Don't say cannot be made, you say cannot be replenished. Renewable resources can be replenished. Don't say can be made, can be reused. You say can be replenished, right? So if you think about it, if it's windy one day, you can't reuse that wind again, right? But what it can be replenished. Recycling, okay, again, it's just kind of sort of common sense really, isn't it? Reduce, reuse, recycle. Now, life cycle assessment, all right? Now, this is then another one of those topics, a big topic, right, that could quite easily come up as a decent sized question. Okay, right. Now, what you need to do if they start talking about life cycle assessment, you have to, honestly, you have to remember 5 things. You have to remember that the life cycle assessment starts with raw materials. Okay, and what they're likely to do, they're likely to give you a something, right, that then you've got to talk about a life cycle assessment. And often what it'll be a comparison between 2 things. Okay, and what you're then going to have to do is you're almost going to have to come up with a bit of an argument, right, a bit of a discussion about potentially which is the best. Okay, now on here I've got plastic bags and paper bags. Now they should probably be the ones that you've talked about at school. Okay, and what you have to do is you've got to think about almost like an analysis of which is actually the best. Okay, and you have to break it up into these 5 individual stages. You start with the raw materials. Now, if you think about plastic and paper, the raw material for plastic is crude oil. Okay, so that's obviously an issue straight away. The raw material for plastic bags is crude oil. It's a finite and we cannot replenish it. The raw material for a paper bag is trees. Okay, so in a way that actually sounds good. So that's kind of like a winner for paper bags. Then you need to think about manufacturing. Okay, how do we actually manufacture? And we need to think about energy. Which one takes the most energy to manufacture? So plastic bags, they require fractional distillation that we've talked about. They're going to use crude oil to do it. And what it's kind of saying here is it's actually relatively cheap to to actually manufacture a plastic bag. Then you've got to think about whatever thing they give you. Manufacturing could be pulping the paper. So you get your trees, you turn it into a mush, you add loads of water to it, and then you heat it up, you crush it, you crush it, you crush it. That actually produces quite a lot of sulfur dioxide and waste. In a way, if we're actually thinking about this as a life cycle assessment, paper wins the first one, but then paper doesn't win the next one. Because the actual manufacture of a plastic bag is quite easy compared to a paper bag. Distribution is then, how do they get to you? Okay, now plastic bags and paper bags are probably distributed from another country in the world. Think about how they actually get there. If you've got a plastic bag in, I don't know, Dubai, right? It then needs to go on a plane, it needs to go on a boat, and then it needs to make fuel to get to you, right? And then the facts that they may well give you will then make you think about whether it's good or bad. Distribution of a paper bag. Chances are it's probably, I don't know, Brazil. Okay? And again, the paper bag then needs to be made, it needs to be transported, it uses energy to then get to you. Use phase. Right? Again, life cycle assessment, you've got to think about the advantages, disadvantages. You've got a cheap 10p plastic bag, you might use it 4 times. Okay? If you buy one of the more expensive plastic bags, you might use it 50 times. If you get a paper bag from Primark, okay, I challenge anybody to tell me that they actually made it home with the paper bag intact. Okay? Because they are so bad. Okay? Especially if it's raining. All right? So, a paper bag, not really reusable. Plastic bag is. Okay? So what you can do here is you can think a life cycle assessment is a bit of an analysis about what you've actually got to do. Okay? Or whether it's good or bad. End of life. What can you do with it? You can recycle it. Okay? But quite often you don't. They are biodegradable. So in a way, paper bags win that one. Okay? Now, just back to life cycle assessment. I don't know what they're going to give you, right? If they do give you a question, but there's a pretty good chance it's going to be kind of like an argument and analysis between 2 different types of substance. But you need to remember raw materials, then manufacturing, then distribution, then use, and then end of life. So whatever 2 subjects or 2 things they give you, you need to talk about each one of those steps, right? And if it is an evaluate question, which it could well be, at the end, you then need to say, I believe the paper bags are the best. I believe the plastic bags are the best. Okay, so don't forget an evaluate question, you need to come up with an answer. Okay, right, there's about 5 more things. Okay, right, potable water. Potable water is water that is drinkable. Okay, now the water that is in the UK is potable water, we can drink it. Okay, I could go anywhere in the country and I could just drink the water out of the tap, that's potable water. If I went to France, I could probably drink it, but I might feel a little bit off because the way that their water is made up is going to be slightly different, right? Now, you just got to remember that potable water is not pure water. It's not 100% water, all right? It has dissolved solids in it, okay? But the dissolved solids are small enough that it makes it drinkable, okay? Now, this is then where it links back to that required practical right at the very start. All right. So if you then think about that required practical, we tested for pH, we tested for dissolved insoluble salt or dissolved solids. So if you remember that what you did is you got your water sample, you heated it up to see how much solid was in it. If there's too much solid in it, it is not potable. If the pH is wrong, it's not potable. Okay. Next one. How do we make potable water? Okay, so what you'll do is you'll pretty much get a river, and from that river, I'll change the colour there because it doesn't show up very well on that. You get a river and the water goes in. When the water goes in, it goes through large kind of filters, okay, and it takes out all the big chunks. So you've got a river, it goes through a big filter, takes out the logs and the fish and the toads and bodies and things like that. It then goes through another filter until you've got quite cleanish water. It then sits in a sedimentation tank where any kind of solid matter sinks to the bottom. So number one, water goes through a filter. Number two, it goes through a coarse filter, which is kind of similar. It's a bit like sand. Number three, it goes into a sedimentation tank where the solid matter sinks to the bottom and it's left there for a little bit. Then it goes into the sedimentation tank. You've actually got anaerobic bacteria in there. And the idea of the bacteria is to then break down some of the solid matter. Number four, it goes into a fine filter. That is then to get rid of anything else that kind of may well be in there. Number five, it gets chlorinated. So as the water goes across, chlorine is added to kill any bacteria that is in there. Then it goes into a tank and then it goes to your house. Okay? So that is literally how they make potable water to go into your house. Water from a river, from a lake, from a reservoir, through filters, coarse filters, sedimentation tank where the chunks sink to the bottom, anaerobic bacteria go in to get rid of some of the sludge, fine filter it, chlorine, sometimes they might use UV light as well, into a tank to your house. Okay, that's the sort of the places like the UK and America and places like that, Europe. Okay. If you're in somewhere ridiculously hot where you don't have your own sources of water, to actually do potable water in these places, they often use the sea. Okay, now you obviously know that if you drink seawater, it's going to make you ill. Okay, so with the potable water in hot countries, first thing they'll do is they will screen it, which is basically filter it. They'll put it through finer filters. Now, the key to this one then is they will do reverse osmosis. Right? So now, if you remember, osmosis is the movement of water from a high concentration to a low concentration. Reverse osmosis means they put it into the kind of the same situation when you've got a little membrane, but they put it under pressure. So the pressure forces the water in the opposite direction. So following on from reverse osmosis, what it does is the salt and other impurities are left. And then what you do is you get your pure water that is then drinkable. Okay? And again, talking about places like Iran and Saudi Arabia and stuff like that, a lot of the missiles that they'd made were hitting the desalination plants, which are these, so that then people didn't have enough water. Okay, so this is a method for making potable water, and it's called reverse osmosis. Sewage, okay, I don't know why I've made that so small. Okay, so it works very much the same as your potable water. Okay, so what you do is your sewage arrives. So after this, you all go for a wee, right? You all flush the toilet. The toilet, all the water goes down a pipe about that big, right? Then it goes to kind of the end of your street and it goes to a bigger pipe. And then at the end of that next street, it then goes to a bigger pipe that can be like a meter high. Then it gets to the kind of the sewage works, which is your pumping station, and it's screened. That is then where they take out any kind of big lumps. You know, if somebody's like flushed a plastic bag down the toilet. It then gets sedimented, which is then sat there. Same thing before it gets biologically treated, where the lumps and the chunks are broken down. Then it's sedimented again. Then they put chlorine, ozone, or UV through it. Chlorine is a disinfectant, it kills it. UV is also something that's used to kill bacteria. Then there's also ozone, and ozone is O3, is also bubbled through it, which kills bacteria. Once that is then done, so then they've killed all the bacteria, it then goes into the river. Okay, and then when it goes into the river, what it does, it goes down the river, it then gets taken into another place where it gets turned into water for you to drink. Okay, that's sewage. Okay, right, so system for sewage, screening, large chunks, primary treatment, get rid of the sludge, liquid, get it bacteria digested, sterilize it, UV, chlorine, or ozone, and then the sludge is then used, and sludge is often used for putting on fields as fertilizers. Right, that's it. That's all the content. Okay, now I'm pooped. Okay, now what you now need to do is, if you're combined, you need to go away, right? This PowerPoint that I've then just gone through is on Google Classroom. Go through it again, right? And if there's anything that's kind of list-wise, right, that I've then talked about, learn it as a list. Okay, but the most important required practicals are those 4, right? Which is all of them. Okay, because any of them could come up. Remember, disappearing cross, the key to it is solid sulfurs made. Analyzing water, this is then where you got your potable water, which is your pH, and your solids that are dissolved in it. If potable water isn't potable if its pH is wrong and it's got too much solid. Chromatography is about RF value, and it is all about solubility. Concentration of acids, difficult one, right? Because what you could do is you could get asked about concentration of acids, and you could get asked about reaction rates. All right, and what they're going to do is they're going to chuck in some sort of practical where you're going to have to work out which is the fastest reaction. And the fastest reaction is one that gives off the most bubbles the quickest. Okay, right, that's it. Right, so at the end of this, what I'm going to do is the kind of session is recording. Okay, it takes about an hour or 40 minutes at the end of it to actually then turn into a video. Right, I will send a link out on Google Classroom. Right, so then if you want to then look at it again, then you can look at it again. Right, and then like I say every single time at about 8:15, right, if you have any specific combined questions, log back on, right, and then I'll probably still be here, right, and then you can ask anything or just send me an email. All right, so good luck everybody, combined. Okay, number 5, then I will see you on Sunday night for the final physics. Okay, and then it's not going to be just Mac, who I can see, it's going to be everybody. Okay, right, so unmute if you've got any questions, or go and have a wee, think about sewage and potable water, right, and then have another look at it all. Okay.
Bye.
Thank you.
Bye.
Goodbye.
Thank you.
Very
Thank
much,
you.
everybody. Right, I'm going to go for a wee, and then I want to see 7 faces. Come on, faces on. Don't be shy. Thank you, Farhan. Adam, come on. Zishan, come on. Daniel, come on. Right. Zara, on Sunday, your camera is working, as is yours, Bawaji. Right. Got it. So, Zara, did you hear that? You've got to get it fixed by Sunday. Okay. And you, Bawaji, no excuses.
I'll try.
No, you will try. I know you'll try.
Yeah.
Okay, you will without fail. Okay, and Bawaji, I don't want to see the top of your head either. Okay, when you get your camera fixed. Okay. Right. So what we're going to do now is we're obviously going to go through the separate stuff. Okay. And there's a fair bit of it. Okay, but it's reasonably okay. All right. So firstly, we'll start off with a bit of organic. Okay. So in the other bit, we talked about the general formulas for alkanes and alkenes. Okay. Now, what I've got on the screen there now is the general formulas. In addition to that, is for your alcohols and your carboxylic acids. Okay. Now, they don't tend to ask them particularly very much. All right. But again, you just never know. Right. So if you don't know them, right, then I would hope that you're going to know the alkanes and the alkenes, right? But if you don't know them, right, I would write down the alcohol one and particularly the carboxylic acid one. Okay. Right. Now, naming, again, I went through it before, right? Relatively useful, okay? Meth, eth, prot, bute, pent, okay? The homologous groups, okay, the groups that then are your triples, where you got ane, ene, ol, and oic acid. Okay, again, they should be pretty straightforward in your brains. Okay, now just going through some of the individuals, we'll start off with the more straightforward ones, your alcohols. Okay, properties of alcohols, right? So what they originally are, or initially, the first five are clear, colorless liquids. Okay, so obviously you're all familiar with kind of ethanol. Okay, methanol is quite a scary substance, really. Sorry, I'm just going to turn it off a sec. I'll put it back on in a second. I'm just going to change the setting. Okay, so methanol, right, and ethanol, right? Obviously, everybody's aware of ethanol, kind of in your vodka and your wine and stuff like that. Now, methanol is actually very, very dangerous. Okay, now I don't know if you remember in the news, it's probably last summer, right? There was people dying in Indonesia where, because methanol is actually very cheap and it's very easy to get hold of, certain bars in Indonesia, they were swapping the ethanol for methanol, right? And what they were doing is they ended up killing people. There's about 7 or 8 tourists that died from methanol poisoning. Sad story as well. I did my degrees in Manchester, okay, and I can remember walking around the streets in Manchester, and I can see some of the people that lived on the streets with brown all around their face, okay, and it ended up that what they were doing is they were going into shoe shops, they were nicking shoe polish, and they were eating the shoe polish because within that shoe polish there was methanol, and the shoe polish got them a little bit drunk. Okay, but it ended up that it ruined their eyes. Okay, so tip, right? Don't eat shoe polish. Okay, just in case you're ever interested, just don't eat it. It's got methanol in it. Right? Again, ethanol is also a poison. It's toxic and it's actually quite dangerous. How do we make it? Anaerobic respiration, right? So again, don't forget, it's not just respiration. Okay, it is anaerobic respiration. And if you look in that top left-hand corner on the screen there, right, there's some kind of demijohns. All right. Now, it's not particularly very clear, okay, but the way those demijohns work is what you have, it's a bit like a toilet system, really, where you have that at the bottom there to prevent its oxygen actually getting in is actually water. So what happens is the bubbles from the fermentation go up that tube there. This is water, the kind of the blue bit here. The carbon dioxide bubbles through it, and then the rest of the carbon dioxide comes out here. But the idea of that system then is to prevent oxygen getting in. Because if you get oxygen going in, it then becomes aerobic respiration, and then the yeast then don't produce the ethanol. Right? So it's the same as your toilet system. Okay. Right, that's fermentation. Right. How do we then get a concentrated solution of it? Okay, so if you ever want to make vodka, right, go to your shed, right, get a round bottom flask, pour a bottle of wine in it, okay, heat it up. The ethanol boils at approximately 80 degrees C. That then boils, goes into your condenser, and then you get pure vodka or pure ethanol coming out. If you were then going to make your vodka, then what you do is you kind of put herbs and spices in with it, and then you would then turn it into the vodka. Okay. Now, as a little tip, that is highly illegal. All right. You're not allowed to distill your own spirits, even though you can make your own wine. Right. Now, on to sort of more difficult things. Well, not necessarily more difficult, but more kind of separates. Right. We've got our carboxylic acids. Okay. That is methanoic acid. Okay. If I was going to draw C double bond O, single bond O, H, and C there and C there, and I then put H's all around that, what would that be called? Okay, so I've got 3 carbons there, and I've got my OOOH group there. Dishan, what would that be called if I got 3 carbons? I hear you.
What do you see, sir?
What did I say? No. Wash your ears out, lad. Right, that there is called methanoic acid. If I do exactly the same structure, and this time I put 3 carbons there, okay, so there's a carbon there, a carbon there, a carbon there. What do we call that?
Ethanoic acid.
Not ethanoic acid, right? If I've got 3 carbons, what does 3 carbons make?
Propene.
It does make, well, propene is where you've got an
Propane.
alkene with a double bond. So it is pro something. So what will it be?
It'd be propane.
Not propane, right? Come on, propane. So propane is an alkane. Okay, propene is an alkene. Okay, that'll have a double bond in it. Farhan, go on, what is it?
It is propanoic acid.
Propanoic acid, right? So you've got propane, an alkane, propene, an alkene. Propanoic acid is 3 carbons with the functional group sticking out the side of it. All right. Okay. Zishan, what if I did C to C to C to O to H? Okay. And I put hydrogens on them. What would that be called? What is it if you've got an OH group on the end?
It is Is it alcohol?
It is an alcohol. So what would the name of the alcohol be?
Pro Propanolic.
Well, just propanol, right? Remember ethanol? Propanol.
Yeah.
Okay. Right, so chemical properties, carboxylic acid, that is their functional group. Okay, often called organic acids, right? Because they are also, you know, the fatty acids that you get from breaking down fats. The fatty acids are carboxylic acids. They have the COOH group, right? They are unpleasant and they are not flammable. Okay, so the carboxylic acids. And we pretty much know they're an acid because of the H on the end. Okay, there is some of the namings of them. Now, I don't really quite know how they're going to ask much about this. Okay, they could draw it and they could maybe get you to name it. Okay, it's just a difficult one about what they could do. Okay, right. With carboxylic acids, right? Some of the uses, you make soaps with them. Okay, fabrics are also used or made using carboxylic acids, and preparing esters, okay, because esters are then more useful, right? The original soap that people used to use probably 50, 60 years ago was purely from animal fat. Okay, does anybody know what they used to mix with the animal fat to actually make soap? I can remember actually doing this as a practical in school until it got banned. Okay, Adam, do you know what they mixed fat from an animal with to actually make soap? No? Anybody nod if they know? It used to be sodium hydroxide. Okay, so they used to literally get sodium hydroxide and then they used to mix it with animal fat and they used to make soap. Right? So next time you're in school, right, get some sodium hydroxide, put it on your arm. Okay, just pour it on, just for a laugh, you know, it's not that bad. Okay, rub it. You've got fat underneath your skin. And what happens is your fat underneath your skin is a carboxylic acid. Sodium hydroxide reacts with the fat underneath your skin. And if you rub it enough, it froths up. And you've actually made your own soap. Okay, sodium hydroxide and carboxylic acid. Right?
So,
Right, now, obviously the big reactions, right, that kind of need to be talked about are esters. All right? So an ester is then mixing our carboxylic acids with our alcohol. Okay, that is called esterification. Should have got you to pronounce that one for you, shouldn't I, Zishan? Okay, esterification. Okay, right. Now, what I'm going to do now is I'm just going to kind of go through sort of what happens and then a little bit of kind of the naming again. Okay, so we've got here is esters. Now, if you think about it, I've got an alcohol, which is, it kind of breaks there. So I've got my alcohol on the right-hand side, and I've got my carboxylic on the left-hand side. So I've got my alcohol, and I've got my carboxylic acid. Okay. Now, when you then react them together, what you are also making is you're also then making water. So you've got your alcohol, so that loses a H, okay, and you've got your carboxylic acid that loses an OH. The O, the H, and the H combine together to then make your water. Okay, so if you think about it, I've got C to O to O to H, and a double bond O there. That's supposed to be a C. It's not a very good C. So that is my carboxylic acid. I've then got my alcohol, which is H to O to C. So that is then kind of my functional group for my alcohol there. That is then my functional group for my carboxylic acid. If those two combine, I lose that, that, and that, which then is H2O, which then makes my water. And then I get my ester. All right. Now, naming. So what I'm going to do now is just take that off, and then we're going to name it. Oh, it took me ages to kind of think about of this one. So what we've got then is over here, right? the first component of this ester's name, the methyl, is from the methanol. Okay, so even though I've drawn it kind of with the red on the right, the alcohol is what gives it its first part of a name. The second part is from the carboxylic acid. All right, so whatever the alcohol is the first part, whatever the carboxylic acid is the second part. Okay, so another example down here. What I've got there is I've got propanol, which is the first part, propyl. And the second part there is my carboxylic acid with 2 carbons, ethanoate. Right? And what I'm going to do in a second is I'm going to ask somebody to name me something. Okay? Right. So I'm just going to get the camera up, okay, which I haven't used at all yet. Okay, now on here, what I'm going to do now is I'm going to combine butanol and we'll do ethanoic acid. Okay, so totally out of focus. What I'm going to do, and backwards. So what I'm going to do in a second is I'm going to ask somebody, if I've got butanol, right, and I've got ethanoic acid, what is the ester I make? If I've got butanol, sorry, and ethanoic acid, what is the name of the ester? That's another one. I'm going to ask, I've now got hexanol and butanoic acid. What am I going to make? Okay, Adam, first one. What am I going to make? Butanol and ethanoic acid. What's my ester?
Butyl ethanoate.
Butyl ethanoate. Good. Daniel, if I've got hexanol and butanoic acid, what's my ester?
Is it hexyl butanoate?
Hexyl butanoate. Correct. Okay, so just remember that and remember the way around it is because it's quite easy to get those wrong. All right. Okay, now a few other kind of combinations to make our esters. Ethanol and propanoic acid, we get that. So remember, that bit there is our alcohol. That bit there is our ethanoic acid. That is our propanoic acid. That there is our alcohol. That there is our carboxylic acid. Okay, wouldn't surprise me, if they don't ask you the naming of something. All right, so just remember the right-hand side, away from the double bond, is your alcohol, and on the other side is your carboxylic acid. Right. Esters. Now, once we've made them, okay, they've got loads and loads of uses. Okay, quite incredible, really, the actual uses. Carboxylic acids are pretty rubbish, right? Alcohols are also pretty rubbish. Now, what you can actually do with esters is, there's 6 things here that I kind of found on a picture. So, food flavorings, explosives, insect repellent, detergents, solvents, and perfumes. Okay, so one of the biggest ones is, again, I don't know if you've ever done it at school, actually made an ester, right? But if you actually make an ester at school, you can actually make, pear drops, that kind of smell of pear drops, right? You can actually make that, right? And it's actually a really, really nice smell if you actually get it correct. So esters can be used for all those different things. Other examples is fruit. Okay, so each one of those fruit produces its own esters. Okay, so pentyl ethanoate, which is pentanol and ethanoic acid, is the smell of pears. Go on, Farhan.
Is that why it can make alcohols
Yes,
like grapes?
that's right. Yeah. That's all kind of part of it. Yeah. Well, no, it actually isn't. It actually isn't. No, that's not the smell. 'Cause, the alcohol from grapes is from the glucose.
Oh, okay.
Because they've got the sweetness in there. That's the glucose that actually makes the alcohols, right? So these are then just kind of the smells that are in. It's a good point, okay, but these are then the smells, right? So a lot of kind of the fruits, okay, then you've then got the smells that then come with it, okay, and each one is slightly different. Right, polymers, okay, so what we're going to do now is we're going to very, very quickly kind of go through some polymer stuff, okay, so natural polymers. Glucose, fructose, monosaccharides. Mono obviously means one, saccharides means sugar. Okay. If we condensation polymerization and we do glucose and fructose, we make sucrose. All right. And sucrose is predominantly one of the main fruit sugars. Okay. Daniel, what's also given off in condensation polymerization? So if I add glucose and fructose and I do condensation polymerization, what else do I make as well as sucrose?
Water.
Water. I mean, it's on the screen there, okay? But think about it, condensation polymerization. So polymerization is where you're making things go together, and the condensation part is the fact that then you're getting water out. Okay, Adam, do you know another natural polymer, right, that is even more kind of these monosaccharides chucked together? Any ideas?
Isn't it like amino acids as well?
Yeah, amino acids
And
works.
proteins, yeah.
Yeah, so amino acids, that is then your monoamines, right, that then kind of combine together, so you can big long chain. But going on to the saccharides, Zara, do you know another condensation polymerization reaction where you got glucose that then gets together by condensation polymerization?
Can glucose also make starch?
Perfect. Glucose makes starch, okay, which is our condensation polymerization. Okay, so I've then got is where's it gone now? There's my mouse. Okay, so glucose can make starch, and glucose can also make cellulose. Okay, so again, if you think about food tests, iodine or microscopes, you've got iodine solution. Okay, that is then part of the reason why cellulose can be found. Okay, cellulose can be stains. Yeah.
Would you also be able to say glycogen then?
I'm not 100% sure of the. Well, yeah, because glycogen is obviously put into place by insulin. All right. So, yeah, so it must be a polysaccharide in itself. Now, I don't know the actual formula of it. Okay, but it must be in there as well. Okay. Right, so that is then our natural polymers, polysaccharides, and then we've got polyamines that are then our proteins. Right, DNA is obviously also another massive, great big natural polymer. Right, so it's a double helix, 2 strands by base pairs. Bawaji, what are the base pairs? Do you know?
You mean like A and T,
That's it. ANT and
GC?
GC. Okay, so DNA is deoxyribose nucleic acid, double strands with base pairs. So adenine and thymine, they go together, guanine and cytosine. So ATGC are the base pairs. Okay, and they are then linked by very, very weak hydrogen bonds. Okay, right. The other polymerization, okay, is addition polymerization, which is a lot harder to do than condensation polymerization. All right. This is then where we have our ethene. All right. Now remember, we talked about ethene previously in all the combined stuff, and I said it was then used in plastics. So polyethene, polythene is then your polymer of ethene. Okay. Zishan, what was the name of the process where we actually made a lot of ethene from the fractional distillation?
Was that not just fractional distillation, is it?
So we had fractional distillation, right? And remember, so we had loads of kind of
Oh wait, it's cracking.
it was cracking. Okay, so cracking is then another good example, right? Where that is then where a lot of the ethene is then made. We then use ethene as addition polymerization with pressure, heat, and catalysts to then make plastics. Okay, so all sorts of plastics are then made with ethene. Okay, done that already, right? Right, polymers, thermosoftening and thermosetting. Okay, I'm going to take them off the screen. All right, and very, very quickly, I'm going to ask somebody what is the main difference between thermosetting and thermosoftening polymers. Okay, right, Zara, give me a property of thermosoftening polymer, please.
They melt.
They melt. Okay. What about thermosetting?
They don't melt.
They don't
They just
melt.
get hot.
Yeah, they don't hot, and eventually what they'll do is they'll just burn. All right. So if you think about the plastic chairs in your school, what they are is there are thermosetting, okay, and the thermosetting polymers, literally, if you heat them up, they'll just burn. The thermosoftening, right, then what you can do, you can reuse them. Okay. Adam, what can you tell me about the bonds in thermosoftening and thermosetting?
The bonds in thermosoftening would be weaker because you are able to bend it and reuse it.
Good.
But setting, they'll be stronger because like you can't actually break them, which is why it burns.
Yep. Do you know what type of bonds they are?
Intermolecular.
Yep. So in thermosoftening, they are intermolecular because it's kind of into between them. Farhan, go on.
I have a question. Yeah, you know, in thermosetting plastics, is it like so? There's like a layer and there's a layer, and then they're like diagonal.
What,
That
as
makes
in
sense.
what? So it's like a layer of plastic, layer of plastic, layer of plastic, and then
So,
other
yeah,
ones.
like black bricks, like
In
I don't know,
thermosoftening or thermosetting.
the one that doesn't burn.
Yeah,
Like,
the thermosetting. Yeah, so it is
yeah.
like that, right? So if I actually just put the information up there, okay, on the PowerPoint I've got, right? So what we've got is the thermosoftening, it can be soft. Thermosoftening structure is got weak intermolecular forces, okay, which is then what Adam said. Now, what you're talking about then, Farhan, is in thermosetting, this is then what I was asking about the bonds, is what they have is they have cross-linked covalent bonds, right? So you're correct. They have like layers, right? It's a bit like, I guess, not an isotope, whatever it is, a alloy. So they've got the layers, and then in between, they've also got covalent bonds that then kind of go at right angles. And it's those right angles that then give it the strength that then it can't melt. Right? Right. Carrying on. There, that's exactly what you were talking about then, isn't it? Okay, so we've got the thermosetting plastics, okay, where you've got the covalent bonds interlinking. Okay, right. Rusting. Right. So again, another topic that was then sort of talked about as something that isn't mentioned particularly very much is the rusting. Right. Now, there's only one metal in the whole world that rusts, and that's iron. Okay. Now, around here, what I've then got is I've got then 4 different methods for preventing rusting. Okay. Now, if you've got a iron gate, the obvious thing to do is paint it. That protects it. Okay. Another obvious thing to do is turn it into an alloy, because an alloy is then going to give it additional strength because you've got the different sort of molecules that are then in it. Does anybody know what galvanization is? Well, Adam?
It's when you cover the iron with zinc.
Yeah. So why
Because
do we do
zinc
that?
is more reactive, so it's able to stop the oxygen reaching the iron.
Correct. Okay. And old metal bins, okay, 30, 40 years ago, they were galvanized, right? So they look silvery, and then underneath they have the iron, which is the strength. What about the cathodic protection? You know what that again, Adam? Do you know what that is? Go on.
Isn't it just the same thing, but with more reactive metals?
It is, but it's put on differently. Okay, so where galvanization is literally where you got a layer of zinc that's kind of almost like forced on, cathodic is then done using kind of electrolysis. So what it is, it's kind of like a more permanent layer around the outside rather than galvanization. All right, so they are then methods for preventing rusting. Right, now what we're going to do is we're going to go through kind of the required practical stuff. Okay, so what I'm going to do in a second is, right, I'm going to ask somebody, because there's kind of 5 parts to this, about the flame tests. What do we do? Okay, now one person is then going to tell me the method about what we do, and then I want to know, people are then going to tell me colours. Okay, so just have 30 seconds to think while I have a swig. Right, Farhan, go on.
No, I had a question. Do you need to know flame photometry?
You need to know what it's all about. Yeah, I've got a diagram of that comes up later.
All right.
Okay. Right, Daniel, tell me what we do in the flame test, please. How do we do it?
So you get your different metal powders, and they're like crushed up, and then you get a nichrome wire, and then you put like the nichrome wire onto the metal powder, and then using a Bunsen burner on a blue flame, you put it like directly above it, and then the color that you get is the color.
Colour, right. Can you give me any examples of any colours?
So like if you put potassium, turns lilac.
Good. Any more?
Lithium turns crimson red.
Okay. Sodium,
Sodium turns yellow.
calcium,
Turns green, I think.
oh, copper's green,
Oh yeah. Orange.
orangey red. Right. Remember with copper, right, copper always kind of relates to green. So if you get cheap jewelry, right, that's got like a very, very thin layer of silver on it, eventually it goes green. So copper's green. Now, there is another way of doing it. You don't just use a powder. Okay, there's another way where you actually get a solution. Farhan?
No, I was just gonna say, don't you have to clean it with hydrochloric acid first?
Yeah, you can. Right. Now, in the method I've actually got, I haven't got it that you clean it with hydrochloric acid, but it does kind of make sense. Okay. Now, there is another way in which you can get your nichrome wire and you can dip it into the powder, but there's also another way if you have a solution. Go on, Adam.
No, I was going to ask, is it like specifically nichrome wires, or can you also use the platinum inoculating loops?
If you're very rich, you can use platinum inoculating loops. Okay.
All
There
right.
there is no reason why, right? It's got to be something that is unreactive. Right, because obviously you're putting a metal on there that is going to react with the actual metal, the wire itself, because nichrome is obviously very unreactive as well. Okay. Now the other way of doing it is you don't just use a powder; you can do it as like a chloride solution. Right. So what you can do, you can have lithium chloride, sodium chloride, potassium chloride. So rather than dipping it into a powder and putting it in the flame, you can dip it into a liquid and put it into the flame. Okay. So they're kind of the two options: powder or a chloride solution. Okay, that's good. Right. Boarji, how do we do the carbonate test, please?
I don't know.
Carbonate test. Zara, carbonate test.
You get your carbonate and you add it to hydrochloric acid,
Correct.
and then you attach it to lime water, and if it is carbonate, CO2 will be produced, and then it will go to the lime water and make it cloudy.
Good. Okay, what's the cloudy bit in it?
Lime.
No, it's not lime. Okay, so the lime water, it's called lime water because of the chemicals that are in it, right? It's actually calcium hydroxide is lime water. Okay, but what is it, the actual precipitate that comes out? Do we know? I mentioned before, it's one of the main things in shells and sedimentary rock. Remember, Zara, I was still talking to you, right?
Is it CO2?
Not CO. Well, CO2 is the actual, obviously, the gas that comes off. But when it goes through the lime water, the CO2 reacts with calcium hydroxide, and it makes calcium carbonate. Okay. Right, yeah, so you're correct. So what you got hydrochloric acid, you then mix it with your carbonate. If carbon dioxide comes off, you bubble it through lime water and it goes cloudy. You've then got calcium carbonate produced. Good. Okay. Adam, sulfate test, please.
Hydrochloric acid, barium chlorides. If sulfate ions are present, a white precipitate will be formed.
Okay, good. And what's the precipitate?
Barium sulfate?
It is barium sulfate. Okay, so the actual precipitate itself, right, is insoluble barium sulfate. Barium sulfate. Okay. Right. Bawaji, do you know the halide test? Bawaji, you know the halide test? No. Farhan, halide test.
Oh, so that. No, I don't really know.
You don't know it? Tara, halide test, please.
You add nitric acid and then silver nitrate, and if it's so there's chloride, bromide, and iodide, and then chloride is white precipitate, bromide is cream precipitate, and iodide is yellow precipitate.
Fantastic. Well done. Okay. Right, you know those very well. Okay, because obviously there's not a huge amount of kind of required practical stuff in this, right? So we've got the flame tests, right? So like Daniel said, you could get a powder on the nichrome wire and then you could put it into your blue Bunsen flame and they're the colors then on the bottom right-hand side, okay? Or you can do it as a chloride solution where you can do exactly the same thing. And then what you'll do is you will then get the same colors that are then given off. Carbonate test. So lime water is calcium hydroxide. Okay, I've written calcium hydroxide at the top there. Okay, and that is then a clear solution. And then what you do then is you add hydrochloric acid and whatever your salt solution is. If there is a carbonate there, you will then get calcium carbonate produced in your lime water. Sulfate test. So then what you got is you've then got your liquid, whatever you're given, you react it with barium chloride with a few drops of hydrochloric acid. If you get your milky white precipitate, that is then barium sulfate. So the barium sulfate is insoluble and it will then appear as a precipitate. Halide test. Okay, I haven't even put the colors on there. Okay, but Zara just told us. So then what we've got is we've got 1 centimeter depth of the sodium solutions or whatever it is in the 5 test tubes, dilute nitric acid, and then add silver nitrate. So we've got dilute nitric acid, add silver nitrate, and if you get a precipitate, you've then got the silver halide formed. Okay, and it could be bromine, iodine, or chloride. Good, right. Now, metals. Now, one of the things I was kind of looking at is where we then just kind of were talking about the metals burning and giving out light. I kind of did one of those research things that I did about stuff that people make a lot of mistakes on that comes up sometimes. Okay. And the question then is, why do the different metals actually give out different colored light? Okay. Now, does anybody know before I start talking about it? Now, this is proper kind of on the verge of sort of A-level stuff. Okay, so it's right top end 7, 8, 9. Right? Anybody know?
Is it
Why
based off
evil?
electrons?
Again, sorry, Zishan?
Is it based off the electrons?
It is based on the electrons. Okay, do you know any more than that?
I know it jumps the electron cells when it reacts with flame. So like you know how copper turns green when it reacts with oxygen? A similar thing happens with a flame test.
You're right on there. Okay, so the reason why a metal ion emits colored light. So we've all done sort of about the electron shells and the electrons that are kind of in certain places. Now, from the transition sort of part, okay, what happens is when they're heated up, the electrons are then given a bit more energy. So if you kind of look at the diagram that I've kind of got on the screen there at the moment, right, what you've got is you've got the electron shells, but if you then heat them up, what happens is the electrons can jump up levels when you actually heat them up. Okay, so when they actually jump up to an extra kind of level, which is something that Combine never even have to think about, what they do then is they then release energy to then drop back down again. Okay, now if you think about it, if all these metals have then got different amounts of electrons, when their electrons jump up to the next level, there are always going to be different electrons that are jumping up. Okay, and then when they drop back down again, they release light. Why isn't my thing not working? Okay, so just to explain that again. So what you have is in those shells there, you've got the transition metals have got electrons. When you heat them up, the electrons jump up a shell. Okay, then when they drop back down again to release the energy they've gained, they give out different colored lights. So for example, when the electrons in copper drop back down, they give out green light. When lithium electrons drop back down, they give out kind of an orangey light.
Sir,
Yep.
and does like the amount of energy released like determine the frequency of that wave, which is why it's that color?
Exactly.
Okay.
So what you got to do is you got to think, because obviously lithium's quite small, isn't it? Where copper is then bigger, right? So it's literally the amount of energy that comes out, which gives the frequency, which gives the color. Okay, hence why they're all different colors. Right? Magnesium, white. You know, you've got all those different things. All right. So that is then our top end 7, 8, 9 bit of information. Okay. All right. So what I've got on there is I've then got just a few other kind of ions that there's probably unlikely to get. Okay. But there are other elements. All right. And what you can do then, you can see that each element is predominantly giving out a different color. Okay, based on the amount of energy that is given out when it drops back down again. Okay, right. Flame emission spectroscopy. Okay, so what we've now got is we've got kind of two different sort of printouts that you can get. All right. Now, emission spectra and spectroscopy. Okay, I can't even say them. Okay. So when each one of those is kind of heated up, what they do is they then give out, based on their electrons, different colors, right, from all the kind of the energy that is then released. So if you think about it, hydrogen has literally only got one electron. So therefore, when it is heated up and it goes through the emission spectra, okay, there's very few lines of light that then can be produced. Where with something more complicated like iron, you then get these lines, all those that are then produced from the iron that is then kind of giving out the electricity, the light again. Now, the reason why this is actually useful is because we can then look at an object that is giving out light, and we can then work out what that object is then made of, which is our spectroscopy. Okay. Right. Rates of reaction. Okay, we talked about this a little bit in our combined one. Okay, so we can chucking some of these in, right? So we talked about, I don't know if it's on that, right? We've got combustion, right? We talked about these as well, right? In the fact of pollutions, right? So carbon dioxide, that causes pollution in the fact of the greenhouse. Nitrogen oxides, Farhan, I can't remember what nitrogen oxides do as a pollutant. What problems do they cause?
Neither do I.
I can actually remember, but I'm like kind of lying. All right.
I don't know, like maybe like they disrupt the nitrogen cycle.
Oh, that'd be lovely if it did. Okay, but possibly not. Okay, Daniel, I'll ask you for laughing.
I'm not sure yet, but is it asthma and like respiratory problems?
Nitrogen oxides, respiratory problems, and also acid rain. Okay, where what they're doing, using kind of the acids in the atmosphere, okay, for acid rain. All right. The nitrogen oxides, predominantly one of the main places they are actually given out is from car exhausts. Okay, because when you've got the actual chemicals and all those kind of things in there, because a car exhaust is very hot and under high pressure, it produces the nitrogen oxides. Carbon monoxide, okay, again, what I did was I talked about that, which is it's combining with hemoglobin, right? And what it does, it makes a permanent bond with hemoglobin, which is obviously dead serious. Let me know why somebody that actually dies from carbon monoxide poisoning actually looks very healthy when they actually die. Anybody know why? Just a random fact that probably won't come up, but it's just interesting. So normally, okay, obviously what you do is you have your kind of normal kind of skin color, right? When everybody dies, what they're going to do is they're going to go a bit paler because the blood is then going away from the surface of the skin. Okay. Now, in carbon monoxide poisoning, when carbon monoxide actually bonds with hemoglobin, it actually becomes bright red. Okay, rather than kind of the red of our blood, right? It becomes bright red. So everybody has a nice red kind of tint to their skin when they actually die, okay, because of carbon monoxide poisoning. Particulates is the carbon in the atmosphere. Sulfur dioxide, main issue with that, okay, it does cause respiratory problems again, but it is acid rain. Okay, right, just on those, okay. We talked about these before. Does anybody have any questions about phytomining or bioleaching? Okay, or can anybody add anything to it that I didn't kind of mention before? Okay,
Sir,
one.
can you go over bioleaching again?
Yeah, so I mean, basically what bioleaching is, what you'll do is you'll get a solution that is very, very high in a certain metal, right? And what they've done is they've developed certain bacteria that if you put it into that, they will then absorb the metal. Okay, and so when those bacteria then absorbing the metal, what they do then is they then eventually get the bacteria out, they dry them, burn them, and when they actually burn the bacteria, what they're then left to is the metal. So it works in pretty much the same way as phytomining, where a plant absorbs the metals, then you burn it, and you got the metal. Bioleaching is exactly the same, where the bacteria absorb the metal, then you burn away the bacteria, and then you're left with the metal. So it's a good way of kind of almost like purifying a solution or taking a metal out of a solution.
So what's a leachate?
What's what?
The leachate.
Leachate.
Yeah, that's what we learnt in school.
What sentence was it in? Tell me the sentence.
I think it's like a solution or something.
Well, I'm guessing that the actual solution itself is the one that you put the bacteria in. Okay, so the leachate, okay, I'm guessing is the. I've never really heard that before, right? I'm guessing it's kind of the solution. Daniel, do you know what was said?
It's like once it's like the solution formed is called the leachate.
Yeah, so the solution that they put the bacteria in is called the leach. Is that right?
Yeah.
Yeah. And then so the bacteria then goes into the leachate, takes the metal out, and then what you can do then is you can take the bacteria away and then you can extract the metal. Go on, Zara.
No, that's it.
All right, okay. Your box went green on my screen again. Okay. Right. We talked again about extracting metals again. So this is then by our electrolysis. Okay. I just wanted to bring this up because obviously phytomining and bioleaching is way more likely to come up on your exam. Okay, because it's more common stuff. Extracting metals again, if you've got a massive, great big, I called it a kebab because obviously a kebab isn't really meat, is it? It's kind of a mass of stuff. So what it is that impure copper anode, you take the copper out and all the sludge then falls off. That's our extracting metals. Okay. Reversible reactions. Okay, again, we mentioned those and we'll talk about the Haber process in a minute. Okay, so reversible reactions means that they can always kind of get to an equilibrium. But obviously Haber process, Le Chatelier's principle is this. Okay, now what I'm going to do in a second is I'm going to ask somebody, right, why when I've got N2, 3H2 and I've got ammonia, what happens if I increase the concentration of nitrogen? What happens and why? And then also, what happens if I increase the temperature of the Haber process? What do I make more of? What do I make less of? Okay, and then pressure. Do I make more ammonia or do I make more nitrogen? Which way does the equilibrium reaction go with pressure? Okay, fine.
Isn't catalyst like a trick question in the
Well, no, the catalyst is there to kind of reduce all the sort of activation energy. What is it? Platinum catalyst? Is that what it is? Okay. No, it's not platinum. I've lost my head. What catalyst is it?
iron?
Iron. Flipping it. Platinum's in a exhaust pipe, isn't it? We've got an iron catalyst, right? So Farhan, do you know what happens if I increase the concentration of nitrogen?
Does the reaction move to the right?
It will. It'll move to the right because I've now got more of that. Okay?
Yeah.
So that kind of makes sense, doesn't it? Right,
Yeah.
Zishan, if I increase the temperature, what happens? I can see your mouth moving.
If it was an endothermic reaction,
Okay, so it's an endothermic reaction. So therefore, if I heat it up, what happens? What do I make more of?
whichever one goes to the endothermic.
Right, well, this is endothermic. So endothermic is that direction.
All right, so it goes to the left.
It goes to the left. So if I increase the temperature, it goes to the left, which is kind of weird, really, isn't it? All right. Adam, I'm now going to increase the pressure. Therefore, if I increase the pressure, what do I make more of? And why?
An increase in pressure is going to favor the side of less molecules, so equilibrium will shift to the right and produce more ammonia.
That's good, right? So then it's kind of a logic, isn't it? Where you've got 4 molecules of gas there, and you've only got 2 molecules of gas on that side. So therefore, if you increase the pressure, the natural reaction is to go in that direction. Okay. Zara, what are the conditions that are actually used in the Haber process?
Temperatures above 450 degrees.
Okay.
An iron catalyst has to be present. and 20 times the pressure, 200 times the pressure.
100 times the pressure. Good. Okay, so then what we've got the Haber process, right? 450 degrees, high pressure, 200, iron catalyst. Okay. What do we need the Haber process for, Daniel?
Wait, I've got a question.
Go on.
You know, when you increase the temperature, why does the equilibrium move to the left?
Because it is naturally an endothermic reaction. So if it's naturally an endothermic reaction, then if you add heat to it, it's going to go in that direction. Okay, so because it's endothermic, you add heat to it, it goes away from where the heat is kind of required.
Wait, so will you get more or less yield if you increase the temperature?
You increase the temperature, you get less yield.
So,
Yeah.
did you say the forward reaction is endothermic?
What, going in that direction?
Yeah.
Yeah, it is. Sorry, my head, I've been talking for the 3¼ hours now. Right, so you're right. Okay, so just rewind. So going in that direction is endothermic because the whole thing is endothermic, isn't it? Right, so the whole thing is endothermic. So going in that direction, right, is then when heat then is taken in. Okay, now I've got a graph that follows on here, and this then shows the results. All right, so when you actually decrease the temperature, you get more. When you increase the temperature, you get less. Okay, so Haber process, if you increase the temperature, you get less. You increase the pressure, you get more. And then you got an iron catalyst.
But sir,
Yep.
If it's endothermic, that means it's taking the heat energy in.
Yep.
And so if there's an increase in temperature, wouldn't it want to oppose the change by lowering the temperature, which would be favoring the endothermic side?
No, I'm just trying to. God, my head has gone to mush. Right? Can anybody explain that? Because my head's gone to mush. Right? Anybody tell me? Right? If you increase the temperature, and it is endothermic, then it is going to go that way. You know what? I don't even think. Who can answer it? Farhan, I bet you can answer it, can't you? No. Bawaji, you're a superhero. So why, if I increase the temperature, do I get more nitrogen and hydrogen? Bawaji, do you know?
No.
Right, I'll tell you what, once I've finished here, I'll look it up and I'll send an email out to everybody because my head stopped working. Okay.
So,
yeah.
If you increase the temperature of a system, it will try to counteract this change by absorbing the extra heat. So, because an endothermic reaction absorbs heat, increasing the temperature will favor the endothermic side.
Okay, well, the endothermic must be that way then.
Okay, that makes sense then, yeah, all right.
Okay, because that's kind of what I said right in the very first place, wasn't it? That the endothermic reaction is that direction. Okay, so therefore, if the endothermic reaction is that way and the exothermic reaction is that way, so basically, if you put nitrogen and hydrogen together, then what you're going to do is you're going to produce heat. So therefore, if you are putting heat in, then it's going to go to the left. So that's what it is, isn't it? Okay, so we'll just clarify that one. Okay, so if you put nitrogen and hydrogen together, it goes that way. Okay, and it's giving out heat. That way is endothermic. So therefore, if you add in heat, it's going to go naturally to the left. Okay, away from the exothermic part. Okay. Right, so there then the graphs for it. Okay, which then shows that the colder it is, the more you get. So then obviously all the conditions that we've then talked about is kind of a comparison, right, to reduce the amount of costs. So obviously, if you put it up above 200 atmospheres, then you would make more product, but the cost is a lot higher, right? Literally, last few little things. Okay, so what we've then got is we've got glass, soda, and lime. So what we've got is we've got a kind of a comparison between different types of kind of glasses. We've got soda lime glass and we've got borosilicate glass, right? Where the soda lime glass is kind of the original glass that you may well have. Okay, and what they were is they were kind of like the bottles that kind of smash. Okay, the borosilicate glass is the stuff that you'll then have in your kitchen, which is kind of the baking stuff, which is then a different type of glass, but what it has a much stronger structure. Okay, so that is soda lime versus borosilicate. Okay, soda lime is very shattery, which is like your glass that you may well break, and the borosilicate glass is more like the stuff that you'll have in your windows. Okay, and you'll have in kind of Perspex or Pyrex equipment. Okay, ceramics have high melting points. They are hard and stiff but brittle, very poor thermal and electric conductors, and are chemically very, very unreactive. Okay, hence why people then used to have ceramic teapots. Clay ceramics, okay, which is basically very, very similar, except they're made from clay. All right, they are made by heating clay at high temperatures, and they are often put with a glaze to then kind of seal them up a little bit. Right. Final thing, fertilizers, NPK fertilizers. So what they have is they've got nitrogen in there, phosphorus in there, they've got potassium in there, which is then our kind of man-made fertilizer stuff. Okay, why do we put them in? Nitrogen is for plant proteins, phosphorus for DNA, and potassium is involved in respiration and photosynthesis. Okay, that's all the theory. I feel quite embarrassed that my brain wouldn't work about the endothermic. Right, so who have you got tomorrow, Daniel? Is it Mr. Tootle? Right, then I'll have a chat with him. Okay. Right. It is bedtime for me. Right. Now, everybody, you need to make sure that obviously you've got the 4 required practicals I taught right about at the start with the combined. Okay. And every single one of you, right, you need to know all those flame tests and all those chemical tests. Okay. So if I ask a question before and you didn't know them, right, you need to look them up because obviously they're going to be on. All right. Think about the exam technique, read the question, right? Because whatever that question is asking, all right, then that is then what you answer. Okay. I'm going to upload the video. Okay. It takes about 30-40 minutes for it to convert into a video from recording this. And then I'll send a link out on Google Classroom if you want to have a look at it tonight or tomorrow or anything that might be there. Okay. Anybody got any questions? All right. Zara, sort out your camera for Sunday. Bawaji, sort out your camera for Sunday. Okay, right. Well, good luck tomorrow, everybody. Right, get a good night's sleep. Lots of monsters in the morning. Okay, that was a joke. Okay, right. I will see you all on Sunday. Well done, everybody.
Thank you, sir.
Bye.
Cheers. See
Bye.
you.
So I have one question.
One.
You know, when you're doing that fractional distillation,
Yeah.
is bitumen the long chain hydrocarbon or short chain hydrocarbon?
Long chain. Right, I'll put it back up for you. Right, let me find it again. It's on the other PowerPoint. Okay. So if I just take off I'll take off the ink, right? Yeah, so what you got is the bottom there. So you got bitumen at the bottom, okay, which is, I know it's probably many hundreds and hundreds of carbons long, right? Because what you got to do is you got to think about the reason why it has a boiling point of 340 degrees. Okay, so it's Mr. Barden's kind of little trick. His kind of little thing is when he talks about spaghetti, right? So if you think about it, if it's got a really, really big long chain, right, then what they're all going to do is all those big long chains are going to wrap around each other. And then what they're going to do is going to have lots and lots of intermolecular bonds. Okay, so that is then why bitumen is very hard to actually turn into a gas, because it has a lot of, it's not strong, it's a lot of intermolecular bonds. Okay, and then when you go up the fractionating column, because then petrol is your shells of pasta, it doesn't have very many intermolecular bonds. So then what you can do when you heat it up, you can break them apart. Okay, do you understand that kind of thing, that kind of concept?
Yeah.
Yeah. Is there anything else
Yeah.
about that?
No, but I've got another question. You know, like, because like tomorrow's going to be like 20% maths in it. So
Yeah.
can they ask about the paper one, like formulas?
No, but they can if they want to, right? But they're not supposed to. But what they do is, and in kind of the guidelines, they say that they can infer or refer to them if it's anything to do with the work that they're doing at the time. Now, I don't think personally they're going to ask about titrations or anything like that, right?
Yeah.
Even though you never know, right? And I don't think they're going to ask about moles. I think tomorrow what you're going to get is you're going to get loads of graph work.
Okay.
All right. But
Yeah.
if you're feeling very, very unconfident about it, then it might be worth just remembering mass equals Mr. Mole, right? And your kind of concentration equations. But I'd be surprised. But then they can also do whatever they want, right? They can even ask you biology stuff if they really wanted to, right? Because there's kind of an expected link between them, right?
Yeah.
So it's graphs, and just take your time with them, right? And also,
Yeah.
don't forget, if you're ever describing a graph, make sure you mention everything on both axes. Don't
Yeah.
just say it's the concentration. You say it's the concentration of this in this. All right.
Yeah.
But yeah, it should be 20% maths. I don't quite know where they're going to kind of get it from, but there will be something in there. All right.
Thank you.
All right. Cheers.
See you.
See ya.